Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Wormholes. Tunnels through space, time, and beyond. A cosmic longing across the void. The night sky has always beckoned with an impossible promise. Every pinprick of starlight that reaches our eyes has traveled across unfathomable distances, a silent messenger from worlds we can barely imagine. We stand here on our tiny planet, looking up, and feel the gulf that separates us from those distant suns and galaxies. It is a feeling both humbling and haunting, an immense loneliness in the face of a universe so vast. Is there a way across this cosmic ocean? In our hearts, a longing takes shape, a yearning to bridge the unbridgeable, to be everywhere that wonder calls us, and to break the limits imposed by space and time. For as long as humans have dreamed, we have refused to accept isolation in the cosmos. Across cultures and ages, our stories have imagined secret paths and hidden doorways in the sky. Myths spoke of gods racing their chariots through the heavens, of enchanted bridges linking Earth to paradise, of travelers riding moonbeams or rainbow paths from one world to the next. These ancient tales all spring from the same source, the deep human desire to connect, to reach out across distance and find something or someone on the other side. In those imaginings, distance was not a prison, but a challenge to overcome with courage or magic. Today, we no longer ride on mythic chariots pulled by celestial horses. Our vehicles are rockets, and our magic is science. Yet the longing remains. We launch probes to the outer planets. We beam radio signals to the stars, hoping for an answer. Still, the distances are cruel. The nearest star beyond our sun is over 4 light years away. Even a message traveling at light speed takes years to get there, and a human spacecraft would require tens of thousands of years. The scale of the universe threatens to keep us forever apart from the wonders we yearn to touch. But what if there is a back door? What if space itself has hidden tunnels, shortcuts that cheat distance and time? What if the universe in all its vastness has secret pathways known as wormholes? In this journey, we will venture into that bold idea. We will follow the path from the dreams of ancient skyfarers to the cutting-edge theories of modern physics. We will step through the looking glass of general relativity and quantum mechanics, peering into the enigmatic tunnels that might bind distant galaxies or even separate universes. Along the way, science will mingle with imagination. We will grapple with equations silently, absorbing their implications without writing them down, translating them into visions and metaphors. We will confront paradoxes of time travel and questions that test the limits of reality. And through it all, a poetic thread will guide us, the voice of our collective awe and wonder, a conversation with the cosmos itself. Picture, for a moment, standing before a shimmering portal in space. On this side, the familiar night sky, the Milky Way's band of stars arcing overhead. On the other side of the portal, seen faintly through its depths, a different sky, perhaps alien constellations or the glowing swirls of a nebula that should be thousands of light years away. Step forward, and in an instant you might emerge there, your foot finding ground under an alien sun. This is the tantalizing promise of a wormhole, a bridge that can unite 2 far-flung corners of the universe as though they were next-door neighbors. It sounds like fantasy, and it may well be. No one has ever seen a wormhole, and they might not even exist. Yet they are permitted by the known laws of physics. In the mathematics of Einstein's theory of gravity, wormholes appear as possible solutions, theoretical tunnels through space-time that could, in principle, connect regions that would otherwise be forever separate. They sit at the edge of our understanding, like whispers from a higher reality. Some scientists believe that if certain extreme conditions could be met, a wormhole might be held open long enough for something or someone to travel through it. Others are skeptical, suspecting that nature has subtle rules, cosmic censorship, some call it, or chronology protection, that forbid such audacity. We do not know the answer, not yet. And yet, the quest continues. Why? Because the stakes are so alluring. A traversable wormhole, if one could be made real, would rewrite the geography of the cosmos. Distance would lose its tyranny. The light years between here and the galactic center, or between our galaxy and Andromeda, would become irrelevant, mere steps through a cosmic doorway. We could visit other star systems not in generations or millennia, but perhaps in a single lifetime, maybe even instantaneously. More profoundly, wormholes tug at the threads of reality in ways that challenge our understanding of cause and effect, space and time. They raise the prospect of time travel, journeys to the past or future, and the mind-bending paradoxes that come with them. They force us to confront whether the universe has an underlying web of connections that we are only beginning to sense, connections that might tie together not just where we are, but when we are, and even what universe we inhabit. So let us surrender to curiosity and wonder. Let the scientific rigor be our compass and poetic imagination our sail. Together, we will explore the story of wormholes, from their first glimmers in Einstein's equations to the latest ideas in quantum physics and string theory, from the challenges of keeping such a tunnel open to the tantalizing hints of how we might detect one out in the starry night. We will ponder what it would feel like to step through a wormhole and emerge light years away. We will wrestle with time loops and parallel universes and ask what all this means for us. Fragile beings who love, hope, and dream. By the end, we'll return to that human longing which set us on this path and reflect on how even the act of imagining these cosmic bridges speaks to something timeless within us. Our journey begins where humanity's fascination with bridging the heavens first took root, in the stories and early theories that tried to break the walls of distance. We leave the comfort of the known shore and push off into the cosmic ocean, hearts full of yearning, eyes open in wonder, asking, are the stars as unreachable as they seem, or has nature hidden a shortcut among them? The dream of bridging space and time. Long before wormholes had a name, the idea of traversing the sky in the blink of an eye lived in human imagination. The ancients stared at the same stars we do, but in their minds, those points of light were not unreachable. They were destinations for heroes and gods. In myth and legend, distance was malleable. A hero might be gifted a pair of winged sandals or a flying horse to vault from one world to another. A deity might descend to earth on a rope of light or a rainbow bridge. Consider the old Norse tales of the Bifrost, a shimmering rainbow said to connect the mortal world of Midgard to Asgard, realm of the gods. Or the Hindu epics describing magical chariots, vimanas, that could soar through the sky and even visit the stars. These were early expressions of a dream, to break the barrier between here and there, to travel without traversing the immense gulf in between. Such stories may seem far from scientific truth, yet they reveal something fundamental about us. We have always been storytellers, trying to shrink the darkness between distant points of light into something we can cross. The dream of instantaneous travel, of portals and shortcuts, is a recurring theme. We whispered it in our fables and wrote it into our fiction as soon as we had the language of science. When technology advanced and we began to grasp the true scale of space, our fantasies did not die. They adapted. In the late 19th and early 20th centuries, writers like H.G. Wells imagined doors in space and time, in tales of time machines and journeys to other worlds, even as scientists were uncovering the real, mind-bending properties of the physical universe. Then came a revolution in our understanding of reality. In the early 20th century, Albert Einstein upended the old, common-sense notions of space and time. His theory of general relativity revealed that space and time are not static, separate backdrops, but a unified, dynamic fabric, space-time. Massive objects like stars and planets curve this fabric, and what we feel as gravity is just objects moving along the curves. Space could stretch, squeeze, and even rip under extreme conditions. Suddenly, the idea of cosmic shortcuts didn't seem entirely absurd. Space-time itself could bend, so perhaps it could bend enough to fold distant points together. Einstein's equations were complex and rich with possibilities. Even Einstein himself did not immediately grasp all the strange implications of his theory. But soon, others began to explore his equations for hidden pathways. One of the first was an astronomer and war hero turned physicist, Carl Schwarzschild. In 1916, while Einstein's work was still new, Schwarzschild found a solution to the equations that described the spacetime around a very compact mass. This was essentially the first theoretical description of a black hole, an object so dense that it creates a deep well in spacetime, a gravity pit from which not even light can escape. At the center of this theoretical black hole was a point of infinite density, a singularity, where the known laws of physics would break down. To Schwarzschild and others, these results were mathematical curiosities. Black holes seemed like an extreme, almost inconceivable outcome. Who could imagine a star collapsing so completely that it punches a hole in the fabric of reality? It took decades for physicists to accept that black holes might actually exist in nature. Yet, hidden in Schwarzschild's solution was something even more fantastical than a black hole. If you extended the mathematics a bit further, you found a strange possibility. Schwarzschild's metric hinted at a tunnel-like structure. In the purely mathematical sense, it was as if the equations allowed the hole to connect to another opening somewhere else. A bit like a tunnel with two mouths, one at each mouth looking much like a black hole from the outside. This was the first glimpse of what we now call a wormhole. In 1935, Einstein himself, along with his colleague Nathan Rosen, took these ideas seriously. They published a paper exploring the idea of bridges in space-time, solutions that connected two regions of space. These came to be known as Einstein-Rosen bridges, essentially wormholes by another name. To visualize it, think of space-time as a great sheet or canvas. Place two distant points on the sheet, say, two stars far apart. Normally, the only way to travel between them is to traverse the sheet, moving through every intervening point. That's a journey that could take thousands of years. But now, imagine pulling those 2 points together, bending the sheet so that they touch, and poking a hole that goes directly from one to the other. The result is a tunnel that bypasses the usual route, a wormhole. Einstein and Rosen's work suggested that under certain conditions, space-time could form such a tunnel. It was a breathtaking concept. Nature might permit a bridge connecting two separate locations, a bit like a shortcut through a higher dimension. One way to picture it is to imagine space as the skin of an apple. An ant crawling across the surface has to go around the apple's curvature to get from one side to the opposite. But a worm burrowing through the apple can take a more direct route, tunneling a hole that opens up far away on the surface. For the worm, the journey is much shorter than the ant's. By analogy, a wormhole is a tunnel through the apple of space-time, potentially allowing something to travel far in a shorter time than it would take going through normal space. However, Einstein and Rosen's theoretical bridge was not a traversable road for travelers. It was more like a precarious tunnel that closes before anything can pass through. Their solution turned out to describe a wormhole that exists only in a fleeting moment of time. It pinches off too quickly. Moreover, it appeared to connect two regions that each looked like a black hole. In fact, what their math really described was an idealized model of an eternal black hole. A black hole that, in theory, connects to a mirror image white hole in another universe or a distant part of this universe. The white hole would be the reverse of a black hole. Instead of pulling things in, it would only spit things out. The Einstein-Rosen bridge connects the black hole and white hole, but unfortunately, it's not the kind of bridge you'd actually want to step onto. If you tried, you'd be crushed by the tremendous gravity at the entrance. And even if you somehow avoided that, the tunnel would pinch shut and you'd be trapped or destroyed as it collapsed. So, in those early years, wormholes were a tantalizing idea, but they seemed to be a cosmic tease, allowed by the mathematics but naturally unstable and untraversable. To the physicists of the time, they were interesting mathematical artifacts more than anything. Einstein reportedly thought of this bridge concept as a way to model fundamental particles, like electrons, as maybe one end of a tiny wormhole whose other end was some other particle, thereby eliminating singularities. It was a clever idea on paper, but it didn't bear out in reality. And so, for a time, wormholes remained in the shadows of theoretical physics. They made occasional appearances in science fiction as a convenient plot device. Long before the term wormhole was even coined, novelists had imagined doorways through space. But serious science had set them aside as nothing more than quirks of general relativity's equations. Yet the seed was planted. The notion that our universe might have hidden passageways was too fascinating to disappear entirely. It slumbered, quietly residing in the equations and in the back of physicists' minds. As decades passed, humanity achieved something once reserved for myth. We began actual space travel, though on a very local scale. We sent rockets to orbit Earth, then astronauts to the Moon. Probes flew outward to our neighboring planets. Each step made the vast distances of space a bit more concrete, and perhaps more daunting. The nearest stars still lay far beyond reach with any technology we could foresee. It was against this backdrop that the wormhole idea was destined to re-emerge, no longer just as a trivial math oddity, but as a serious proposal intertwined with some of the biggest questions in physics. Einstein-Rosen bridges and beyond. By the mid-20th century, the word wormhole had been coined, likely by physicist John Wheeler in the 1950s, to give a catchy name to these hypothetical tunnels. The name itself evokes something crawling through an apple or the earth, making a hidden shortcut. Wormholes moved from obscure journals into mainstream imagination. Still, for a while, they were mostly considered science fiction or extremely speculative science. After all, if Einstein and Rosen's version collapsed instantly, was there any hope of a real crossable wormhole? The next chapter in the wormhole saga came from asking a bold question. What would it take to make a wormhole traversable? If the equations say the tunnel collapses too quickly, is there anything in physics that could hold it open? This line of inquiry took off in the 1980s, led by a few visionary theorists. Imagine you are an engineer of the universe, trying to shore up the walls of a cosmic tunnel so that it doesn't cave in. What kind of scaffolding or material could you use to keep a wormhole stable? This is where things get truly exotic. The answer that general relativity gives is shocking. You would need negative energy or negative mass. In everyday life, we never encounter negative mass. There is nothing you can hold in your hand that weighs 1 kilogram. All masses and energies we know are positive, which produce gravity that pulls inward. But a wormhole's throat, the tube connecting its mouths, naturally wants to pinch closed under its own gravity, much like a heavy tunnel might collapse under its weight. To hold it open, you'd need something that pushes outward against gravity, repulsive gravity, in effect. And that's what negative energy does. It's like gravity with an opposite sign, a sort of anti-gravity pressure. Now, classical physics insists that energy is always positive. You can remove energy from a region, make it cold or empty, but you can't have less than 0 total energy in it. However, quantum physics, the physics of the very small, has some loopholes. In the quantum realm, particles and antiparticles can spontaneously appear out of nothing as long as they vanish quickly. The energy accounting can momentarily go negative in small regions due to the uncertainty principle. There is also a phenomenon called the Casimir effect. where two metallic plates placed extremely close together in a vacuum will actually feel an attractive force due to quantum fluctuations of the electromagnetic field. In between the plates, certain energy modes are suppressed, effectively creating a region of lower than normal vacuum energy. You could call it a pocket of negative energy density relative to normal, empty space. When scientists observed the Casimir effect, they essentially glimpsed a tiny fragment of this exotic stuff that the wormhole theorists were talking about: negative energy. In the 1980s, physicist Kip Thorne and his colleagues, inspired, intriguingly, by a request from Carl Sagan, who was writing a science fiction novel and wanted to make wormhole travel sound plausible, worked out the first self-consistent theory of a traversable wormhole. They wrote down a mathematical description of a wormhole that a human could, in principle, travel through without dying. No crushing singularities, no instantaneous collapse. It was like designing a tunnel through space-time that was as gentle as possible, a sort of U-shaped tube connecting two faraway locations with no deadly forces inside. The catch? Their wormhole model required threading the throat of the wormhole with exotic matter, matter that has negative energy density. In their calculations, the walls of the wormhole tunnel must be filled with something that has an anti-gravitational effect to hold the tunnel open against the natural tendency to collapse. This was a remarkable insight. It connected wormholes to quantum physics and even to speculative ideas about future technology. If some advanced civilization could somehow gather or generate enough negative energy, they might create or stabilize a wormhole. But generating negative energy in sizable quantities is not something our current science knows how to do. The Casimir effect produces only tiny amounts on tiny scales. For a wormhole large enough for a person or a spaceship, the amount of negative energy needed is beyond enormous. It's something for which we have no mechanism. Nature, however, might have its own mechanisms. Some physicists mused that maybe in the early universe, when conditions were extreme, wormholes could have formed with the help of quantum fluctuations, and perhaps some survived. Or maybe some weird astrophysical object could provide the needed physics. For example, certain hypothetical particles or fields might generate negative pressure. Let's pause and digest what this means. By the late 20th century, the idea of wormholes had evolved from a collapsing Einstein-Rosen bridge to the concept of a traversable shortcut sustained by exotic matter. The science community recognized that nothing in the laws of physics outright forbids wormholes. General relativity permits them, and quantum physics provides loopholes to feed them negative energy. However, not forbidden is far from actually real. There were still many puzzles. Could the required negative energy exist in large, sustained amounts? Would quantum effects somehow always balance out so that you can't get enough negative energy in one place without something going wrong? Some research suggested that nature imposes quantum inequalities, limits on how much negative energy you can have and for how long, which might slam the door on making a traversable wormhole, or at least make it extremely difficult. Despite these unknowns, wormholes had transitioned from myth to mathematics to a full-fledged topic of theoretical research. And as our understanding deepened, wormholes became entwined with other profound ideas. They weren't just about fast travel. They started cropping up in discussions about time travel, quantum mechanics, and even the fundamental structure of reality. To see how, we need to delve into what passing through a wormhole might entail and the strange possibilities it opens up. The traversability problem, holding a wormhole open. To truly appreciate the challenge of traversing a wormhole, imagine trying to walk through a tunnel made of rubber that is under tension, trying to snap shut. Each step you take, the tunnel narrows behind you, eager to pinch off. This is essentially what space-time itself would do to any naive wormhole. Gravity pulls the walls of the tunnel together with overwhelming force. Without intervention, the wormhole collapses so quickly that even a ray of light wouldn't make it through from one end to the other. So, what do we need to keep it open? We introduce the idea of exotic matter with negative energy as the hero of this story. But can we be a bit more concrete about it? What does negative energy even mean? One way to think of it is to consider gravity again. Positive mass energy curves space-time in a way that attracts. Negative mass energy, if it existed, would curve space-time the opposite way. Its gravity would repel. If you had a lump of negative mass and you put a normal object near it, the normal object would feel a repulsive force pushing it away. And interestingly, the negative mass would seem to chase the normal mass, a strange quirk of the equations. This kind of material isn't known to exist in any tangible form, but in the wormhole context, we don't need a chunk of negative mass metal or anything. We just need a region where, effectively, the gravitational field is pushing outward instead of pulling inward. The calculations by Thorne and others gave a prescription. Line the throat of the wormhole with a shell of negative energy density. Think of it like reinforcing a tunnel with steel beams, except here, the beams are made of something that creates anti-gravity. This would push outwards on the tunnel walls and keep them apart, preventing collapse. How might one obtain such negative energy? Quantum theory offers some ideas. The Casimir effect, as mentioned, is one concrete example. It creates a tiny region of space where the energy density is lower than the space outside. In effect, it's a negative energy pocket relative to the outside vacuum. Another idea comes from the concept of vacuum energy in cosmology, the energy of empty space that drives the expansion of the universe. If one could manipulate the vacuum energy, maybe it could be made negative in some region. Yet another exotic concept is so-called phantom energy, a hypothetical form of energy in cosmological models that has even more intense properties than dark energy and could violate energy conditions, though this is highly speculative. All of this remains theoretical. To date, we humans have not created negative energy beyond the microscopically small Casimir regions, nor have we found negative mass particles zipping around. But in the realm of theory, some interesting developments have occurred. Physicists have crafted examples, mathematical models, of traversable wormholes that obey as many known laws as possible. For instance, recent studies showed that if you have a black hole with a very strong magnetic charge, it might induce quantum effects that effectively generate negative energy in its vicinity. In one proposal, certain kinds of charged, massless particles in a specific quantum configuration could circulate and create regions of negative vacuum energy, thereby propping open a wormhole. These wormholes, however, turned out to be tiny, like subatomic size, essentially useless for humans, but fascinating as a proof of concept that wormholes might not be totally forbidden. Another line of thought involves extra dimensions, which we will discuss more later. If our universe has hidden dimensions beyond the familiar three of space and one of time, those extra dimensions might allow shortcuts or provide the conditions needed for wormholes without having to violate energy conditions in the traditional way. In some brain world scenarios, where our universe is like a membrane within a higher dimensional space, gravity leaks off our brain into the higher dimensions. This leakage might allow for natural wormholes, or at least less stringent requirements for negative energy, because the geometry of space-time could be different than we expect when it's embedded in a larger reality. Imagine our 3D space is like a sheet of paper, and a wormhole is like a fold that goes into the third dimension, height, to connect distant points on the sheet. If you actually had that third dimension to use, which we normally don't feel in daily life, then maybe forming a stable tube is easier. Even with all these clever ideas, one truth remains. If wormholes exist or can be made, they are not easy things. The universe does not hand out faster-than-light cosmic subway tunnels to just anyone. You have to pay in weird, rare currency, negative energy. And perhaps there are hidden costs we haven't discovered yet. Stephen Hawking, for instance, suspected a kind of cosmic self-consistency. He formulated a chronology protection conjecture, arguing that physics might conspire to prevent macroscopic time travel, which wormholes could enable, because any attempt might blow up the wormhole or otherwise thwart the scenario. More on time paradoxes soon. To step through a wormhole safely, You need not only to hold it open, but also to make sure that tidal forces, the differences in gravity that can stretch and squeeze, are not fatal. If you've heard of how falling into a black hole might spaghettify an object, stretching it into a long strand, that's due to intense tidal forces near the singularity. A well-designed traversable wormhole would have to avoid such deadly gradients. In principle, if the wormhole is large enough and the gravity at the throat is not extreme, a traveler might not feel anything more than weightlessness as they drift through. But if the wormhole mouth is small, approaching it would be like approaching a black hole. The gravity might increase sharply, giving you a wild and possibly lethal ride. In summary, the traversability problem forced physicists to think outside the box of normal matter and energy. It took the discussion from wormholes are mathematically possible but useless to wormholes might be made usable if exotic physics comes into play. This was a huge shift. It turned wormholes into something one could, in theory, engineer, given sufficiently advanced technology or understanding of quantum gravity. It opened a door, albeit a very speculative one, to imagining actual journeys through a wormhole. And that invites the question, what would such a journey be like? Before we address the experiential side, let's consider how far we've come. We started with human longing, passed through myths, saw how Einstein's theory gave birth to the idea of wormholes, and confronted the fact that they tend to collapse. We introduced exotic matter as a lifeline to hold a wormhole open. The stage is set. Now, let's step through that stage into the hypothetical reality on the other side of an open wormhole. In the next section, we'll leave equations aside for a moment and engage in a thought experiment. If a traversable wormhole existed, how would it look and feel to those who approach it and pass through it? Inside the cosmic tunnel, anatomy of a traversable wormhole. Imagine you are an intrepid explorer in a future where humanity has managed, against the odds, to stabilize a wormhole. Perhaps it was found naturally adrift in space, a relic of the early universe that we managed to tame with technology. Or perhaps it was manufactured through processes that today we can only dream about. Either way, you are now in a spacecraft approaching one mouth of this wormhole. What do you see? From a distance, the wormhole mouth might resemble a black hole. It could appear as a dark, spherical shadow against a backdrop of stars. Around it, you might see a strange distortion of light. Stars behind the wormhole could appear warped into rings or halos, due to the gravity of the wormhole lensing the light. In fact, one distinctive signature of a wormhole versus a black hole might be that you could potentially see light coming through it from the other side. Instead of an utterly black silhouette, the wormhole might have a shimmering interior if the far end opens near some bright region like a nebula or a star. Some theoretical models suggest a wormhole could produce a double image or a ring of whatever lies on the other side. As you draw nearer, the view gets stranger. The star field ahead might start to duplicate or warp radically. Imagine looking straight into the mouth. You could be gazing into a funnel where the far end's environment is visible in a compressed, fisheye view. Around the rim of the mouth, the normal universe's stars might appear smeared into a ring, an Einstein ring effect. It would be as if a piece of another sky is embedded in our space, framed by a gravitational mirage. Your vessel's instruments would note gravitational forces, but if this is a well-behaved wormhole, you don't feel a deadly pull. You carefully align your ship to enter. It's crucial to go right through the center, much like threading the eye of a needle in 4 dimensions. If you veer too close to the edge, the throat walls, gravity could pull you against them and crush you. But let's assume expert navigation. Crossing the threshold of the wormhole mouth, you might not feel anything particularly special at that exact crossing. There's no physical gate or membrane, just a region of intense gravity and exotic effects. Suddenly, the outside universe's view is behind you, perhaps as a pinprick shrinking away. You are now inside the wormhole throat, the tunnel between universes or distant locations. What is it like inside a wormhole? The truth is, we don't know, but we can speculate based on the mathematics of space-time curvature. If the wormhole is large enough, the ride could be surprisingly smooth. You might be in free fall, weightless, not feeling acceleration, much like an astronaut orbiting Earth. The walls of the tunnel are not physical surfaces, but a region of space where curvature is extreme and supported by that exotic matter we discussed. There might be some radiation present, perhaps from particles that wander in or from quantum effects at the throat, so the inside might glow faintly, or it might be dark if nothing is there to emit light. If the wormhole is short, you transit in a flash. For example, you could imagine a wormhole connecting 2 points a few light years apart, but the length of the tunnel itself might only be, say, a few billion kilometers. You might traverse that in a matter of hours at moderate speed, or even minutes if you coast through. In some science fiction, wormholes are depicted as instantaneous teleportation, vanish here, appear there. But a traversable wormhole still has a finite length inside, albeit possibly shorter than the external distance. So you might actually travel through a corridor for a little while. The most mind-bending aspect, however, would be what happens with time and simultaneity. If both ends of the wormhole are stationary, relative to each other, and in shallow gravitational fields, you might not notice anything unusual about time. You leave at 1 o'clock and arrive a little after 1 o'clock because the travel path was so short. But if the wormhole ends are in different gravitational potentials or have been moved around, for example, one end is on a fast-moving spaceship, time could be offset. You might come out and find that clocks on the other side are out of sync with those on the side you entered. This possibility leads to the time travel paradoxes which we will discuss soon. For now, let's focus on the sensory and physical experience. One could imagine looking out the window mid-transit. What would you see? Potentially, you might see the entrance you came from shrinking behind, surrounded by a ring of light from the universe you left. Looking forward, you could see the exit growing, with the target universe's starfield expanding. There might be a region in the middle of the journey where vision is very strange. Some theorists talk about a cavity of highly curved space where light can actually wrap around, and you might see multiple images of anything inside, or even see your own ship's taillights ahead of you, due to light curving around the tunnel and coming back. It could be a visual kaleidoscope, an echo chamber of light. Now imagine the moment of exit. One instant, you're in the tunnel, mostly surrounded by darkness and the memory of the stars you left. The next instant, a whole new vista blossoms before you. It could be startlingly sudden, like stepping out of a cave into daylight. If the wormhole opens near a star, that star's light will flood the tunnel as you come out. If it's in deep space, you might emerge into a view of a galaxy that is oriented completely differently from the one you left. Perhaps you're now thousands of light years away, looking at constellations that are alien to you. You check your navigation instruments and confirm it. You have arrived at the other side of the wormhole. The distance that would have taken an unthinkable journey outside, maybe crossing entire swathes of the galaxy, took only a short passage inside this tunnel. To summarize the anatomy, a wormhole has 2 mouths, also called portals or ends. Each mouth might look like a black hole externally, but without an event horizon trapping you. In a traversable wormhole, effectively, the event horizon is either non-existent or has been altered so you can go both ways. The mouths are connected by a throat, which is the space inside the wormhole. The throat's spatial length can be anything from a tiny distance to arbitrarily long, but for a useful wormhole, we want it short relative to the external separation. The throat must be sustained by some form of exotic structure, negative energy, to prevent collapse. If that sustenance fails, the wormhole could either pinch off, leaving 2 isolated black holes, or 1 black hole and 1 white hole that quickly ejects its content and closes. Or it could violently explode, implode, either way destroying anything inside or at the mouths. In a well-constructed wormhole, tidal forces can be small. That means you wouldn't necessarily be stretched or crushed. It could be like floating in gentle space. However, near the mouths, there could be strong gravity gradients if the mouth is small. What about communication through a wormhole, not just travel? If the wormhole is open, you should be able to send light signals through it. That means you could shine a flashlight into one end and it would emerge out the other, perhaps with some distortion. You could have a conversation with someone on the far side, like a telephone line, by sending light or radio signals back and forth through the tunnel, with effectively no time delay beyond the transit through the throat. If the wormhole is short, that would be nearly instantaneous, even if the mouths are light years apart externally. This raises a profound implication. Wormholes allow information to defy the normal speed of light limit for journeys through space. You still can't send information faster than light through any one region of normal space. But the wormhole provides a shortcut route, so effectively, you beat a beam of light that tries to go the long way outside. Before we get ahead of ourselves, it's worth noting that being inside a wormhole might not be quiet and peaceful. There could be weird radiation. There might be quantum effects like Hawking radiation if the wormhole mouths have some properties akin to black holes. Also, if the wormhole connects very different environments, say one mouth near a star and another in intergalactic space, there could be flows of matter. Gas might be drawn through, or cosmic rays might funnel in. A traveler might see a faint glow, or feel a flux of particles. But let's assume our wormhole is clean and well behaved. Emerging from the wormhole, one also wonders, is the trip one way or can you go back? A traversable wormhole, by definition, should allow two-way travel. That's in contrast to, say, a black hole to white hole connection, where you could only go one direction, into the black hole and out the white hole, never backwards. With exotic matter maintaining the throat, you should be able to reverse course and go back through the wormhole the way you came, effectively returning to your original location and time, depending on circumstances. It would be a round trip shorter than a photon could have done in normal space. What about the edges of the wormhole mouth? If you try to go around a wormhole mouth in normal space, you'd just circumvent it, like going around a spherical mass. There's no event horizon, so you could in theory orbit a traversable wormhole like any massive object. Perhaps one might station a ring-shaped space station around the mouth at a safe distance, acting as a gateway port. People or ships could approach, line up, pass through, and then, on the other side, another station could receive them. It's fun to imagine the engineering. You'd probably mark where the wormhole mouth is in space with beacons, because visually it might be confusing since it distorts light. We've now lived out a small hypothetical, journeying through a wormhole and seeing what it's like. It sounds almost serene in our description, but underlying it is a titanic achievement of physics. To go through a wormhole safely, we essentially had to assume new physics, exotic matter or similar, and an understanding of quantum gravity that we currently lack. We also assumed nothing went terribly wrong, no collapse mid-transit, no violent gravitational spasms. It's clear that wormholes blur the line between science and fiction at this moment. We simply don't know if such an experience will ever be possible. But thinking about it yields insights. For instance, it emphasizes how wormholes allow faster-than-light travel through the shortcut, but not local violation of physics. A person in the tunnel always moves slower than light locally. It also hints at why wormholes might enable time travel, which we should discuss now. We mentioned that if one mouth's clock is out of sync with the other, one could possibly travel not just across space, but across time under certain setups. Let's unpack that next, because it's one of the most paradoxical and profound implications of wormholes. Loops in time, wormholes and time travel paradoxes. Wormholes, if they exist, don't only challenge our notions of distance, they can also shake our understanding of time. We all have an intuitive sense of time's flow. Cause precedes effect. Clocks tick forward uniformly for all. Aside from Einstein's known effects of relative motion, or gravity. Time travel has long been a staple of science fiction, usually treated as something distinct from space travel. But in relativity, space and time are intertwined. A wormhole is a spatial shortcut, but under relativity, a shortcut in space can become a shortcut in time under certain circumstances. How could a wormhole allow time travel? The key is something called a closed time-like curve, which is a fancy term for a path through space-time that loops back on itself, meaning if you travel along it, you end up at the same point in space and time, effectively returning to your own past. Normally, such loops aren't present, at least at macroscopic scales. In our universe, they are mostly the stuff of thought experiments, but wormholes open the door to them. Here's a thought experiment to illustrate. Suppose we have a traversable wormhole with two ends, A and B. Initially, they are synchronized in time. Clocks at A and B both read, say, 12:00. Now, if nothing else is done, going through the wormhole from A to B is just like stepping through a door. You arrive essentially at the same time you entered, maybe a few minutes later, because you traveled through the tunnel. No time travel yet. However, now let's take end B on a journey. Put the B mouth on a fast-moving spaceship and fly it around at high speed, near the speed of light, or take it on a trip near a strong gravitational field. Then bring it back near A. Einstein's relativity tells us that moving clocks or clocks in deep gravity run slower relative to those that stay put. So when B comes back close to A, its clock might be behind A's clock. Perhaps B's clock now reads 11 o'clock, while A's reads 12 o'clock, meaning B's mouth has experienced time 1 hour less than A's due to time dilation. Yet, because the wormhole connects them, the connection disregards the external time difference. Now what do we have? We have wormhole mouth A at local time 12 o'clock, and wormhole mouth B at local time 11 o'clock from its perspective. If you enter mouth B, the one that experienced less time, at what B considers 11:05, you might come out of mouth A when A's clock says 12:05, but B's 11:05 corresponds to an earlier moment on A's timeline, because B's clock is behind. Essentially, you would emerge from the wormhole at A at a time before you entered B. In other words, you traveled back in time by an hour as measured on A's side. This is tricky to describe without a diagram, but the result is famous. A wormhole whose ends have been moved around relative to each other can become a time machine. You could go through in one direction and come out in the past of where and when you started. If you go the opposite way, from A to B in our scenario, you'd go an hour into the future relative to entrance time. So the wormhole allows an asymmetry. One direction is a trip to the past, the other to the future. What can you do with such a time-traveling wormhole? Theoretically, you could send information or objects to the past. This raises all the classical paradoxes. The grandfather paradox, what if you go back and prevent your own existence? Or the bootstrap paradox, what if you bring back information or an object that has no origin because it was passed from future to past in a loop? Wormholes don't automatically allow unrestricted time travel to any era. They link specific times and places, the times at which the wormhole mouths exist. So, for example, you couldn't use a wormhole created in the year 2200 to go back to 2025 if the wormhole didn't exist in 2025. But you could potentially go back to when it was created or first opened. Physicists have poured a lot of thought into whether these paradoxical situations could actually happen. Some have concluded that any attempt to create a time loop with a wormhole would result in conditions that destroy the wormhole or otherwise prevent the paradox. One idea is that radiation would build up. Imagine a simple scenario. You try to send a bit of light, a photon, through the wormhole to the past. If the alignment is just right, that photon could emerge in the past and potentially do something like nudge a mirror that ensures that same photon ends up going into the wormhole again. Now, if each loop amplifies the number of photons, say it triggers an emission of 2 photons that then go back, you might get an exponential pileup of energy, effectively an infinite feedback loop, as the photon circles through the time loop over and over, all cramming into the same moment. Calculations show that when you approach a configuration where wormholes would allow backwards time travel, these feedback effects can become infinitely large, suggesting the wormhole would get blasted apart by the energy surge. This is related to Hawking's chronology protection idea. Even if physics doesn't explicitly forbid a closed, time-like curve, the universe might protect itself by making the conditions unphysical, like requiring infinite energy, or by destroying the wormhole when it tries to form a time loop. Other physicists argue for consistency. Maybe time travel can happen, but you could never create a paradox because the only histories that survive self-consistently are those where events already account for the time travel. This is known as the Novikov self-consistency principle. In simple terms, if you go back in time, you might become part of history rather than changing it. For instance, you might attempt to prevent an event only to realize that your interference is what caused it, or that something always thwarts your efforts. The timeline would somehow find a way to avoid inconsistency. That's a more philosophical stance and hard to test, but it's not mathematically ruled out in relativity. If wormholes were available to actual beings, the temptation to use them as time machines would be huge. It could be wonderful. Imagine being able to see the past, or send warnings backward, or retrieve lost information. Or catastrophic. Someone could try to tamper with causality, or accidents could spawn loops that we can't foresee. We might have scenarios of multiple timelines or parallel histories if one interprets quantum mechanics that way. Perhaps each paradoxical attempt splits off a new branch of reality, a many-worlds interpretation applied to time travel. So you can't truly change your original world's history. You only create a new, divergent timeline. Alternatively, perhaps any attempt to change the past simply results in the same outcome, keeping the timeline consistent. The ethical and practical implications are enormous. We will talk about ethics soon, but focusing on physics. Wormhole time machines are extremely speculative, but not outright forbidden by general relativity alone. It's quantum mechanics and maybe deeper principles we don't yet know that might intervene. Indeed, many experts suspect that once we have a full theory of quantum gravity, it will show that traversable wormholes or wormhole time machines can't actually form under realistic conditions. Some recent calculations in string theory and other advanced frameworks hint that perhaps traversable wormholes require special setups that aren't naturally occurring or easy to engineer. And even if they exist, maybe they can't be turned into time machines due to subtle quantum effects. Nonetheless, as a thought exercise, wormholes have taught us a lot. They've forced physics to confront what-if scenarios about time travel in a logically rigorous way. The consensus, so far, is, if nature allows time loops, it keeps them hidden well. We haven't seen any evidence of tourists from the future, or messages from tomorrow, unless one day we realize some phenomenon was exactly that. It could be that wormholes exist, but nature prevents using them to go back before their creation. A kind of limited time travel that doesn't break causality globally, or they might be completely ruled out by something we have yet to discover. Time travel paradoxes make for great storytelling and headache-inducing physics discussions. One famous example often cited: if you have a wormhole time machine, could you go through and shoot your earlier self before you entered, thus preventing yourself from going in? That's a classic paradox. In a consistent universe, something would prevent the situation from happening exactly that way. Perhaps the gun misfires, or you find you simply cannot bring yourself to do it. Or you shoot, but only wound, and end up causing the very scar you saw on your older self that motivated going back. The universe might enforce self-consistency, or timelines might branch into parallel worlds, rather than truly changing a single history. This possibility of parallel worlds brings us to another fascinating lens through which wormholes can be viewed: quantum mechanics and entanglement. It turns out that the equations and concepts that produce wormholes in relativity have surprising analogues in the quantum world, and understanding one could illuminate the other. Invisible bridges, wormholes, and quantum entanglement. In the 1930s, the same year Einstein and Rosen published their idea of wormhole bridges, Einstein-Rosen or ER bridges. Einstein was also involved in another famous paper with Podolsky and Rosen on a completely different topic, quantum entanglement, often abbreviated EPR after the authors. Entanglement is the bizarre quantum phenomenon where two or more particles become linked, such that the state of one instantly influences the state of the other, no matter how far apart they are, as if they share a connection outside of normal space. Einstein found this spooky action at a distance deeply unsettling. It took many decades, but experiments repeatedly confirmed that entanglement is a real feature of our world. If you create a pair of photons or electrons in a certain quantum state, then separate them by miles, they behave in ways that defy classical explanation. Measuring one seems to instantly affect the other, in correlation, even though no signal passes between them, at least none that we can detect, and none that obeys normal speed limits. It's as if entangled particles are dancing in unison across any distance, without communicating in the usual sense. For a long time, entanglement was just a quantum oddity, something to be accepted and perhaps harnessed, as we do now in quantum computing and cryptography. But some physicists began to notice a curious resonance between the properties of entanglement and the properties of wormholes. Both seem to suggest some kind of deep connection between distant points. Could these two be facets of the same underlying reality? This line of thought gained momentum in theoretical physics, especially around 2013, when two prominent theorists, Leonard Susskind and Juan Maldacena, boldly conjectured ER equals EPR. In plain language, that proposal suggests each quantum entangled pair of particles may be connected by a tiny Einstein-Rosen wormhole bridge. They didn't mean there's an actual tunnel you could traverse between those particles. These would be extremely tiny and non-traversable wormholes, so you couldn't send a person or even a photon through them. Rather, it was a way to reconcile how entanglement could have such immediate correlations without traditional signaling. Perhaps, in some higher dimensional sense, entangled particles are adjacent, connected by the equivalent of a wormhole that shortcuts through an unseen dimension of space-time. This idea remains theoretical and somewhat speculative, but it has intriguing support in certain advanced theories, like the holographic principle and string theory. For example, in certain simplified universes, toy models that physicists study, like a universe with a negative cosmological constant used in holographic duality, it's been shown that you can have two black holes that share a single interior because they're quantum entangled. That interior is effectively a wormhole linking them. If you have two black holes maximally entangled, it's as though they form a single connected system via an ER bridge. Why does this matter? Because it hints that space-time geometry and quantum entanglement are deeply related. Some even suggest that space-time itself could be woven from quantum entanglement threads. In other words, the unity of space, the fact that space feels like a continuous whole, might arise from the vast network of entanglements between all the microscopic constituents of the universe. If entanglement is like invisible filaments connecting particles, and if each such filament is a tiny wormhole, in a mathematical sense, then our space might literally be the product of these connections. It's a poetic and mind-expanding idea. The fabric of space-time may be stitched together by quantum threads of entanglement, and wormholes are the geometrical picture of those threads. This concept also provides a new way to think about black hole puzzles. There's the famous black hole information paradox. If a black hole gobbles up information, say someone falling in with a diary, what happens to that information when the black hole eventually evaporates via Hawking radiation? Quantum physics says information can't be destroyed, but it seemed like black holes might violate that rule. Some resolutions using the ER equals EPR idea suggest that Hawking radiation particles, the ones that escape a black hole, are entangled with what's inside, and by extension connected via tiny wormholes. So perhaps information isn't lost at all, but rather subtly transferred out through those connections. This is still a hot research area, but it's amazing that wormholes found relevance in it. Additionally, recent experiments, though very rudimentary, have tried to simulate wormhole-like behavior in quantum systems. In late 2022, a team of physicists reported using Google's Sycamore quantum processor to simulate a tiny wormhole. They engineered a system of entangled quantum bits, qubits, that behaved analogously to two minute black holes connected by a traversable wormhole. By sending a simple message into one side, in the form of quantum information, and seeing it emerge on the other side, they in essence demonstrated teleportation via an entangled wormhole. Of course, no actual space tunnel was formed. It was a mathematical analog within the quantum computer. But this experiment shows that the ER equals EPR idea is more than philosophical. It can inspire real tests that deepen our understanding of quantum gravity, bringing wormholes out of pure speculation and inching them toward empirical science. Stepping back, even if every entangled pair has a wormhole, is too literal a statement. The emerging theme is that space and connectivity might be an emergent phenomenon. The distance between two particles might be partly a function of how entangled, or not entangled, they are with the rest of the world. Perhaps everything in the universe is much closer in some deeper quantum sense. Like pages in a book seem separate in 2D, but are adjacent in 3D when bound together. It's almost philosophical. Maybe what we perceive as empty space between objects is just a manifestation of most things being only weakly entangled. If we could see the true quantum connections, perhaps no two objects are ever truly isolated.
In simpler terms, one could say quantum mechanics offers invisible threads, and general relativity offers tunnels, and they might be describing the same phenomenon in different languages. When you marry the two, you get a richer picture where geometry, like wormholes, and quantum connections, entanglement, unify. Understanding this unity might be key to formulating a theory of quantum gravity that so far has eluded science. Furthermore, this interplay between entanglement and wormholes suggests new avenues for experimentation. That recent quantum computer simulation is one example of how these ideas are moving toward the realm of testable science. It was a very toy model of a wormhole, but as quantum technologies improve, we might simulate more complex wormhole scenarios in lab systems, giving us insight into how real wormholes, or the underlying principles, might work. This quantum perspective leads naturally to the idea of extra dimensions and string theory, where wormholes might find a more comfortable home. If entanglement hints at hidden connections, string theory takes it a step further by positing actual hidden dimensions of space in which wormholes could exist. To fully appreciate that, we should step into the world of higher dimensions, a place where our imaginations and equations venture beyond the 4D space-time we directly know. Wormholes and higher dimensions, the string theory view.
The concept of wormholes fits intriguingly well with the idea that there may be more dimensions to space than the three we experience. String theory, a leading though unproven framework for a theory of everything, requires extra spatial dimensions. In some versions, as many as 6 or 7 additional dimensions curled up at tiny scales. If these extra dimensions exist, wormholes might be more than just theoretical oddities. They could be natural geometric features that involve those hidden dimensions. Think back to the analogy of a 2D creature on a sheet of paper, for whom a wormhole might just be a mysterious door that teleports them. But in our 3D view, we see it as a tube that goes off the sheet. In the same way, perhaps what looks impossible or singular in our 3D space is easily done by curving through a 4th or 5th spatial dimension. One popular brain world idea, brain meaning a membrane-like universe, is that our entire universe is like a 3-dimensional surface embedded in a higher dimensional space, often called the bulk. In these scenarios, it's been shown that gravity might propagate through the bulk, while light and matter are mostly stuck on the brain, our universe. If gravity can seep out, perhaps it can also find shortcuts. Indeed, some researchers have found that in certain setups like the Randall-Sundrum model, a specific 5D model addressing why gravity is weaker than other forces, you could get stable wormhole solutions without needing exotic matter as weird as in pure 4D relativity. Essentially, the higher dimensional geometry itself does the trick of sneaking around energy condition violations. You might have a wormhole that appears to violate 4D rules, but actually it's perfectly fine in 5D. It's just borrowing an extra dimension to sustain itself. Imagine two distant regions on our brain, our 3D sheet. In normal 3D, they're far apart. But if you can go through the bulk, the higher dimension, maybe they're not so far. Like 2 points on the surface of a table are far in 2D, but a shortcut through the third dimension, above the table, could connect them by a direct straight line through the air. A wormhole might just be a manifestation of our space bending through that bulk to join those points. String theory also introduces new objects, strings and brains, that could potentially form or stabilize wormholes. For example, there are hypothetical entities called D-brains and fundamental strings. One might imagine a configuration where a string or a brain is arranged in such a way as to link 2 points. There is research on D-brain wormholes, where the wormhole is essentially a byproduct of how brains are shaped in higher dimensional space. Another interesting stringy concept is that black holes and wormholes might be closely related through dualities. In certain cases, a wormhole solution in higher dimensions can, when viewed in 4 dimensions, look like a pair of charged black holes or other exotic objects. This is quite technical, but the gist is, higher dimensions open up a whole menagerie of possible shapes and connections for space-time. Wormholes, which in 4D require weird stress energy, might be natural geometric features in 5D or beyond. Thus, discovering a wormhole might indirectly indicate evidence of extra dimensions, a thrilling possibility that would revolutionize physics.
There's a more speculative notion still. Wormholes connecting not just different places in our universe, but different universes entirely. In some cosmological models, our Big Bang might have spawned multiple bubble universes, separate regions of space-time that never meet. Usually, each bubble is isolated, but a wormhole could be a tunnel between such otherwise disconnected bubbles. If string theory's picture of a multiverse of brains is true, perhaps one mouth of a wormhole could lie on our brain, our universe, and the other mouth on a neighboring brain universe. That would be literally a portal to another universe.
String theory also suggests that at extremely tiny scales, the Planck length, 10⁻35 mem, space-time is not smooth, but frothy or filamentary, echoing Wheeler's quantum foam idea. In that foam, mini wormholes might constantly flicker in and out. Most would be inconsequential, but some theories muse that a few could have been inflated or stabilized somehow. For instance, if a tiny wormhole formed during cosmic inflation, one mouth could have been whisked far away while the other remained near, effectively stretching the wormhole. Or if certain high-energy events, like cosmic string interactions, assuming cosmic strings exist, occurred, they might create small wormholes. If micro-wormholes exist today, they might be all around us at Planck scales, but imperceptible. Some advanced technological civilization, or future humans, might dream of capturing a tiny wormhole and enlarging it, a bit like grabbing a tiny soap bubble and inflating it without popping it. Science fiction as that sounds, it's a scenario that's been contemplated in theoretical papers, using intense fields or special quantum effects to coax a wormhole to grow. So far, string theory and related ideas have not provided definitive, yes, wormholes are real, and here's how to make one, answers. But they have enriched the conversation, showing that under certain conditions, wormholes aren't just mathematical freaks, but plausible structures in a richer cosmic setting. They've tied wormholes to fundamental puzzles like why gravity is weak, maybe because it spreads into extra dimensions, which also allow wormholes. They've linked wormholes to potential signatures like unusual gravitational effects in our 3D world, hinting at hidden dimensions. And if string theory is right about extra dimensions, wormholes might be out there doing subtle things. For example, if gravity can travel through wormholes, two regions connected by one might exert slight anomalous gravitational influence on each other. Some scientists have proposed looking for such anomalies. One idea was that the supermassive black hole in the center of our galaxy could be a wormhole. If so, stars orbiting it might feel tugs from stars or mass on the far side of the wormhole, in whatever region or universe it connects to. As we'll see, people have actually looked at the orbits of stars near our galactic center for unexplained deviations that might hint something invisible is pulling from a mirror world beyond the wormhole. So far, no clear sign, but the fact that we can even make such a test is astonishing. Having journeyed through general relativity, quantum theory, and higher dimensions, you might wonder, are any wormholes actually out there? Or are they all talk and no show? It's a hard question, but scientists have pondered how we might detect a wormhole if one exists in the cosmos. Let's explore what clues we could search for in the sky and whether any hints have turned up. Unstable gateways, tidal forces, and other challenges.
A traversable wormhole, should one ever exist, would be a precarious structure. It's like walking on the knife's edge of physics. One wobble, and the wormhole could collapse or morph into something decidedly non-traversable. We've already mentioned some threats: the requirement of negative energy, the possibility of time travel-induced feedback, etc. Now let's gather those and other challenges to paint a picture of just how delicate a wormhole would be.
1. Tidal forces and gravity, gradients. If a wormhole throat isn't large enough or well constructed, anything entering may be subject to intense tidal forces. For example, if one end of the wormhole is near a massive body and the other is not, the gravity difference can cause huge stresses. Ideally, one might position wormhole mouths far from massive objects to minimize this, e.g. in interstellar space. But even then, near the mouth, space-time curvature is high by definition. That's what bending space into a tunnel entails. If you've got the negative energy balancing things, you might neutralize some of that. But any imperfection could mean one side of your ship feels a slightly different gravitational pull than the other side. And if that difference is too high, it's like the forces near a black hole. You get spaghettified, stretched and squashed. The bigger the wormhole, mouth radius, the gentler the tidal forces can be. So a key engineering goal would be making the wormhole throat as wide as possible for safety. 2. Radiation and vacuum fluctuations. The interior of a wormhole might not be empty. Space is never truly empty. There are always quantum fields fluctuating. In a wormhole, these fields might behave in unusual ways. Some might get blue-shifted, increased in energy, as they travel through the wormhole, especially if one mouth moves relative to the other, as in the time machine scenario. You could have a situation where what starts as harmless vacuum fluctuation becomes high-energy radiation when it emerges out the other end, or bounces back and forth gaining energy. For instance, if one tries to turn a wormhole into a time loop, the vacuum fluctuations looping through might amplify and destroy it, the feedback we discussed with Hawking's idea. Even aside from time loops, cosmic radiation, like high-energy particles, gamma rays, etc., might enter a wormhole mouth. If one mouth is near an active environment, say near a star or a galactic center, and the other mouth is in a quieter region, radiation will pour through from the active side to the quiet side, potentially exposing travelers or equipment to bursts of energetic particles. A stable wormhole might need radiation shielding, or some way to dissipate energy buildup. Perhaps the exotic matter itself helps reflect or absorb it. Otherwise, the interior could heat up or develop dangerous levels of radiation that either collapse the wormhole or harm whatever goes through. 3. Collapse and pinch-off. The exotic matter must be present and arranged just right. If something disturbs it, say it disperses, gets neutralized, or shifts, the wormhole could begin to close. How fast? Possibly at the speed of light or near it. A traveler partway through could be caught as the tunnel pinches down. That might crush or sever them if the collapse is catastrophic. Imagine the throat narrowing like a closing sphincter while you're inside. You might be compressed or stranded in a fragment of space disconnected from both ends. Maintaining the exact conditions for an open throat might be like balancing a pencil on its point, doable with active stabilization, but if your stabilizer fails, down it goes. This is why some theorists suspect traversable wormholes, if they exist, might be extremely transient or require continuous control, like an ongoing application of negative energy from some generator. 4. Quantum instabilities. There are suggestions that wormholes might be inherently prone to quantum instabilities. For example, could they facilitate processes that normally are ultra-rare or forbidden? One wild idea: wormholes could potentially trigger vacuum decay. If our universe's vacuum state is metastable, a possibility in some particle physics models, a wormhole might provide a shortcut for it to decay to a lower energy state, which would be catastrophic, essentially a bubble of true vacuum expanding at nearly light speed, erasing normal matter and structures. This is very speculative, and most think it unlikely, but it underscores a point. Messing with space-time might have unknown side effects. Even if vacuum decay isn't a concern, wormholes could cause other exotic phenomena like particle production. The strong bending of space might polarize the vacuum and spawn particles, sort of like Hawking radiation. Over time, this could sap energy from the wormhole or flood it with radiation or exotic particles, like an uncontrollable vacuum laser or something. Such issues mean a wormhole might naturally evaporate or shrink as it radiates energy away, unless fed somehow. 5. Interference and interaction with surroundings. Even if a wormhole stands stable in a pristine environment, the universe around it won't stay quiet. It might drift near other masses or be perturbed by passing gravitational waves, like those from distant black hole mergers. Could a strong gravitational wave shake a wormhole and cause oscillations or collapse? Possibly. Wormholes have resonant modes, like any gravitating system. If a wave hits the mouth, the throat might wobble. In a scenario where someone is traversing during such an event, it might be like an earthquake in the tunnel. Also, if humans start using wormholes regularly, there could be traffic management issues. What if too much mass goes through at once? Shoving a huge amount of mass through a wormhole could alter the stress-energy balance and momentarily strain the exotic matter's ability to hold the throat open. Perhaps each transit slightly destabilizes it. You'd need a cool-down period or active damping systems to keep it open after heavy use. 6. Decay over time. Even a theoretically stable wormhole might not be eternal. Maybe it slowly leaks its exotic matter, or quantum effects cause the exotic state to degrade. Over a long time, millions of years, a wormhole could gradually contract or pinch off if not maintained. If civilizations rely on wormholes, they'd have to monitor their health, a kind of infrastructure maintenance. Imagine a far future scenario where a forgotten wormhole network starts collapsing because the generators keeping them open fail. Star systems could become isolated again, or travelers could be lost mid-route. Given all these hazards, any journey through a wormhole would be taken with great caution. It would be like crossing a bridge made of glass over a chasm, hoping it doesn't crack under your weight. One would likely send probes first, measure conditions, possibly actively stabilize the wormhole with some engineered device, like feedback systems injecting bursts of negative energy or adjusting the throat geometry on the fly to counteract perturbations. Perhaps using a wormhole will always remain a delicate operation, not a casual stroll. On the flip side, understanding these challenges is useful. Each of them suggests a way to test or constrain wormholes' existence. For instance, if wormholes tended to collapse with too much mass, maybe none above a certain size could survive, which might tell us why we don't easily see them. Or if they radiate, maybe we could detect an unusual radiation spectrum from what looks like an isolated black hole. So far, we have no direct evidence that any of these speculated issues have manifested in reality. But then, we haven't found a wormhole either.
It might be that if nature allows wormholes at all, they exist only in realms we haven't observed, like at Planck scales or in extreme conditions, or are carefully hidden by cosmic censorship of a sort. The bottom line: traversable wormholes would be high-maintenance, temperamental beasts. They're the divas of theoretical physics, requiring special conditions, throwing fits if stressed, possibly self-destructive if you break their rules. But if one could tame such a beast, the rewards are immense. Knowing these caveats, we can now turn our attention to the practical side of things. How might we detect a wormhole if one exists out there in space? After all, it's one thing to theorize and simulate on a quantum computer, but finding a real wormhole would shake the foundations of science. Let's explore what signs or signals a wormhole might give us, and whether scientists have already looked for them. Searching the skies, how could we find a wormhole? Despite wormholes being theoretical, scientists have pondered ways they might reveal themselves if they exist in the universe. After all, if nature did leave a few wormholes around, perhaps formed in the Big Bang or by some exotic process, they might interact with matter and light in noticeable ways. One obvious effect: gravitational lensing. Gravity bends light, as predicted by Einstein and confirmed by many observations, like the famous image of an Einstein ring, where a galaxy's mass distorts the light of a more distant quasar into a ring. A wormhole mouth, having mass and gravity, would also deflect light, but it could do more than a normal mass. Light from a background object could potentially go through the wormhole and come out the other side. So an observer might see weird things, perhaps 2 or more images of a distant star or galaxy, one from light that went the normal long way around, and another from light that detoured through the wormhole. For instance, if a wormhole connected 2 different regions of the universe, we might observe a double image of a celestial object, or an Einstein ring with an unusual shape. Astronomers have actually considered this. They worked out that a traversable wormhole could produce a unique lensing signature, basically a pattern of Einstein rings or arcs that is distinct from what a lone black hole or galaxy would make. One study suggested a wormhole might create 2 concentric rings of light from a single background source, one ring from light that skimmed the outside of the throat, and one from light that passed through and exited the other mouth. Detecting such a double ring would be smoking gun evidence. So far, no confirmed observation of that nature exists, but surveys of gravitational lenses could, in principle, stumble on an odd case that matches a wormhole's fingerprint. Another clue could come from motion of objects near a suspected wormhole. For example, the center of our Milky Way hosts a massive compact object, almost certainly a black hole, Sagittarius A. We have observed stars orbiting extremely fast close in. One idea, put forth by a few researchers, was, what if instead of a black hole, Sag-A is actually a wormhole mouth? How could we tell? They proposed that if it's a wormhole connecting 2 places, there might be matter, or stars, on the far side, whose gravity can leak through. That could add a subtle wobble or perturbation in the orbits of stars on our side. Specifically, one study suggested that a star orbiting our galactic center might feel an additional tiny pull, as if there were an unseen mirror star orbiting the wormhole from the other side. If our instruments reached enough precision, we might detect a deviation in the known orbit, which is otherwise explained perfectly by a single central mass. Researchers calculated what sensitivity is needed, and it's extremely high, though future telescopes might approach it. If such an anomaly were found, and other explanations like another small black hole were ruled out, it could hint at a wormhole. There's also the possibility of catching exotic emissions. Consider that a wormhole connecting 2 different environments might have matter flowing through. Imagine one mouth is near an active galactic nucleus with hot gas and radiation, and the other mouth is in a quiet galaxy. We might see high-energy particles suddenly appearing from empty space near the quiet galaxy's mouth. Basically, stuff shooting out of nowhere, from the perspective of that galaxy. This could look like a spherical outburst
or an unusual radiation source with no obvious power supply. Some astrophysicists speculated that certain unexplained phenomena could, with a lot of imagination, be wormholes. One example, the so-called odd radio circles, ORCs, discovered in recent radio astronomy surveys, giant ring-like radio emissions in the sky with no clear counterpart in visible light. They are likely shock waves from galaxy interactions or remnants of some burst. But one hypothesis was, maybe it's a wormhole's sphere of influence. In that interpretation, a wormhole might cause a spherical wave of radiation, say from matter colliding as it enters a mouth, which we'd see as a circle, since we see the cross-section of a sphere from far away. This idea is very speculative, and ORCs are still under study with more mundane explanations, but it shows people are thinking about how wormholes could manifest. Another potential sign, gravitational waves. If two black holes collide and merge, LIGO and other detectors can catch the resulting gravitational wave signal. If wormholes exist, especially if they can form or oscillate, they too could emit gravitational waves. For instance, if a wormhole oscillates, the two mouths moving relative to each other like a spring, it would radiate gravitational waves. Or if something falls through a wormhole, the throat might vibrate and emit a burst. These signals might have distinctive echoes. Some theoretical work suggests that if black holes have interior wormhole structures or other exotic compact structures, after the main merger signal, there might be a series of faint echo pulses as gravitational waves bounce around inside the structure and leak out. Scientists have looked for unexplained echoes in LIGO data. There have been tentative claims, but nothing conclusive. Most in the field treat those with caution. Still, as detectors improve, gravitational waves could either reveal surprises or put tighter limits on exotic objects like wormholes. One more arena, the cosmic microwave background, CMB, the afterglow of the Big Bang. If a wormhole formed in the early universe, more on that soon, and it was large, it might have left an imprint on the CMB's patterns. Perhaps a strange symmetry or repetition. For example, seeing the same galaxy or cosmic feature in two widely separated areas of the sky because a wormhole made light paths converge. Cosmologists have searched the CMB for odd correlations, like matching spots or circles, that could indicate the topology of space is weird. Say, space is connected in loops, which would also cause duplicate patterns. None have been clearly found at a significant level. However, they usually weren't explicitly looking for wormholes, more for wraparound universes. A wormhole imprint would be a bit different and harder to differentiate from random fluctuations. It's a long shot, but an interesting one. If wormholes were abundant, we arguably might have noticed something by now. An unexplained lens here, an odd motion there. The fact that we haven't may suggest that if they exist, they are either extremely rare or very well hidden, for example, microscopic, or masquerading as black holes almost perfectly. On the other hand, our observational tools have only recently become precise enough to even contemplate these subtle effects. The orbits of stars at the galactic center, for instance, can now be measured with accuracy down to a fraction of a percent. In the coming decades, any tiny anomalies might start to surface. To summarize, scientists are actively scanning the heavens for unusual gravitational lensing signatures, double rings, unexplained multiple images, watching motions of stars and gas for perturbations that don't fit known masses, monitoring high-energy or transient events, gamma-ray bursts, radio bursts, cosmic rays, for patterns that could hint at matter coming or going mysteriously, listening with gravitational wave detectors for something weird that might point to exotic objects like wormholes, checking the cosmic background for patterns that defy conventional cosmology. So far, nothing has shouted wormhole here, but the search has really only begun. It's akin to looking for a needle in a haystack when you're not sure there even is a needle. But as technology and surveys improve, we might at least constrain the possibilities. For example, we could say, no wormhole bigger than X is present within Y light years, or we'd have seen effect Z. Even that is useful, as it tells theorists what's off the table. Now, beyond trying to find a wormhole, there's a deeper line of inquiry. Could wormholes have been formed naturally at all? We touched on the Big Bang and primordial wormholes. Let's explore that avenue. The possibility that wormholes are as old as the universe, forged in the furnace of creation itself, and perhaps still lurking in the cosmic wilderness. Primordial gateways, wormholes from the early universe. The idea of wormholes often leads to a natural question. If they can exist, could some have been formed in the early universe? Moments after the Big Bang, the cosmos was incredibly hot and dense, a roiling sea of energy and quantum fluctuations. Some theorists have suggested that in this initial quantum chaos, tiny wormholes might have spontaneously appeared and vanished as space itself foamed at the smallest scales. This concept of quantum foam, championed by physicist John Wheeler, imagines space-time at the Planck scale, the very smallest scale, as an ever-changing landscape where little tunnels and bubbles constantly form and dissolve. Most of these would be ridiculously small and fleeting, but what if one somehow got caught in the expansion of the universe? According to inflation theory, our universe underwent a brief period of explosive expansion, fractions of a second after the Big Bang. If a wormhole, even a submicroscopic one, popped up during that epoch, the rapid stretching of space could have blown it up in size as well, potentially to macroscopic proportions. Such a primordial wormhole would be a relic of creation, a carryover from the universe's birth. Unlike wormholes formed by the collapse of stars, which we have no evidence for either, these would be fundamentally ancient structures, predating galaxies and stars, threading through the cosmos from its infancy. What would happen to these wormholes over time? The universe's expansion might pull on them, or they might drift, anchored to nothing in particular. Many might have collapsed quickly if they weren't stable. The violent conditions of the early universe could destroy fragile structures. But some could theoretically survive to the present day, hidden in the vastness of space. They might be very difficult to distinguish from a small black hole gravitationally, unless we notice the peculiar signatures, like the unusual lensing effects or leakage of gravity to another region, discussed earlier. If one exists within our observable universe, it could connect extremely distant regions that were once close together at the Big Bang. Notably, Stephen Hawking and others speculated on the role of such primordial wormholes. Hawking mused that tiny wormholes might constantly be appearing and disappearing at the quantum level, and although most would be too unstable or too short-lived for any use, they hint that space-time is not a smooth sheet, but a restless ocean of possibilities. If inflation magnified a few of those fluctuations, then wormholes may be as much a part of the cosmic fabric as the galaxies and stars, just far harder to detect. Some researchers have even considered whether primordial wormholes could be linked to mysterious phenomena, like certain unexplained cosmic signals or the seeding of large-scale structures. But as of now, these ideas remain conjecture. In practical terms, if primordial wormholes exist, they offer a tantalizing opportunity. Nature's own wormhole laboratories scattered in space. We wouldn't need to create a wormhole from scratch if we could find and capture one. An advanced civilization might hunt for these ancient tunnels, trying to stabilize or enlarge them for transport. It sounds fantastical, but so does the entire wormhole concept. At the very least, the possibility of primordial wormholes reminds us that wormholes could have cosmic origins. They might not just be science fiction or theoretical solutions on paper, but real artifacts of the universe's birth, waiting eons in the darkness for someone to discover their entrances. Beyond light speed, communication and consciousness. Wormholes aren't just about moving people or ships. They also redefine how we might send information. In a universe without wormholes, no message can travel faster than light through normal space, which means a radio signal to a star 100 light-years away takes a century to arrive. But with a wormhole, communication could be essentially instantaneous, no matter the distance. Imagine a network of wormholes linking far-flung planets. Colonies across the galaxy could speak with each other in real time, sharing knowledge and culture without the tyranny of light-speed delays. It would be the ultimate communication infrastructure, an interstellar internet, where the ping times are zero. The implications for memory and data transfer are profound. A library's worth of data could be sent through a wormhole as easily as passing a book through a door. Archives light years apart could effectively merge into one. One could back up information in a distant, safe location with no delay, providing security against local disasters. Even more striking is the prospect of consciousness travel. While physically moving a person requires transporting their body, one could imagine a scenario where a mind is copied or transmitted. With wormhole communication, perhaps in the far future, a person's neural patterns, their memories and personality, could be sent to another planet and downloaded into a waiting clone or robotic avatar. This would be a kind of teleportation of consciousness. You wake up on the other side of the galaxy in a new body, without your original body ever making the journey. It's speculative, but wormholes make the physical distance the least concerning part of that wild idea. Even without such advanced biotechnology, wormholes could allow something akin to telepresence on an unprecedented scale. Remote exploration robots on an alien world could be controlled in real time via a wormhole link, as if the operators were actually there. Surgeons on Earth could operate on patients in a spaceship light years away by manipulating instruments through a small wormhole window. Friends separated by vast distances could virtually sit in the same room via a tiny wormhole portal, more intimate than any video call, because light and sound would actually be passing through a shared space. All of this hinges on having wormholes to use, of course, and it raises interesting physical and philosophical questions. Information going through a wormhole bypasses the normal route through space, but it still must obey consistency. One couldn't use a wormhole network to send a message to one's own past unless a time-offset wormhole was set up, with all the paradox issues we explored earlier. Engineers of a wormhole communication grid might have to enforce rules, for instance, preventing any wormhole pair from becoming a potential time loop communicator. But within those constraints, the benefits are staggering. The concept of transferring consciousness also forces us to ask, what is the self? If a mind can be projected elsewhere and inhabit a new vessel across the cosmos, are we more than our physical forms? Wormholes won't answer such philosophical queries directly, but they could provide the stage to test them, a way to separate mind from original matter without the gulf of space and time in between. In a way, wormholes might someday let us bridge not only space, but the gap between minds, connecting intelligences across distance in a form of direct communication that makes current technology look like smoke signals. These possibilities exemplify how wormholes, if harnessed, would revolutionize civilization. They collapse not just space, but also the separation between beings. With instant communication and the potential exchange of thoughts or even selves, the universe would feel a great deal smaller and more intimate. It's a future in which distance is no barrier to sharing knowledge or love. A future where the saying, "we're all connected," is physically, literally true. Gateways and guardians, the ethics of wormhole use. If wormholes become a reality, humanity, or any intelligent users, will face serious ethical and security dilemmas. The power to bridge star systems or centuries comes with responsibilities that dwarf those of previous technologies. One immediate concern is control. Who gets to use a wormhole and who decides where and when it leads? A traversable wormhole, especially the first of its kind, could be the most coveted asset in history. Governments, corporations, or other groups might struggle for monopoly over these gateways. After all, controlling a wormhole is like controlling a shortcut through space and time. a strategic high ground unparalleled in significance. We can draw parallels with past innovations. Consider when humans first built ocean-going ships. Trade routes and choke points became sources of immense power for empires. A wormhole route is even more absolute. If you control the only bridge to a resource-rich star system, you essentially control that system without needing a fleet. This suggests that unregulated wormhole use could lead to conflict. Nations might go to war over wormhole access, or a powerful entity might keep a network of wormholes secret to maintain an advantage. To prevent such outcomes, society would need frameworks, perhaps treaties that declare wormholes a common good, or international interplanetary bodies to supervise their operation, a bit like how we treat Antarctica or outer space in current international law, but with even higher stakes. There's also the question of security and misuse. A wormhole can be a doorway for commerce and travel, but also, potentially, a conduit for invasion or catastrophe. An enemy could send troops or weapons through a wormhole, bypassing all traditional defenses. Even a small wormhole could be used maliciously. Imagine someone opening a tiny wormhole in the middle of a city and funneling dangerous substances or deadly radiation through it from a safe distance. On a cosmic scale, one could theoretically divert matter from a star, like a stream of plasma, through a wormhole to threaten another world. Such scenarios mean that if wormholes exist, there may need to be agreements or technologies in place to police their usage, much like nuclear materials are monitored today. Wormhole detectors might be developed to alert if an unauthorized portal opens in a protected area, for instance, or fail-safes to collapse wormholes if misused. The time travel capability complicates ethics even further. If a wormhole network allows forward and backward time jumps by virtue of relativistic transport of one mouth, how do we handle the possibility of altering history? It might become necessary to establish strict laws, e.g., a prohibition on turning a wormhole into a time machine, perhaps enforced by international accord or automatic fail-safes in wormhole generators. One could imagine a chronology protection agency, a nod to Hawking's chronology protection conjecture, either a literal task force or simply the collective agreement of scientists to avoid creating causality paradoxes. People could be tempted to use wormholes to go back and prevent tragedies or gain advantage. Lottery numbers, anyone? Which raises moral dilemmas. Do we allow controlled, consensual changes to history, or is any change a violation of the rights of those who lived through the original timeline? Most thinkers suspect that unrestricted time travel would be destabilizing. Thus, ethically, it might be near universally outlawed, even if physically achievable. Beyond overt misuse, there's the matter of equity. If wormholes are expensive or hard to make, initially only a rich elite or powerful governments might have access, widening the gap between those who can cross the stars and those who cannot. There will be ethical pressure to democratize such technology, to avoid a universe where a few get to gallivant across space-time while others are stuck on their homeworlds. History has shown that with airplanes, telephones, and the internet, widespread access eventually became key to unlocking the full benefit of the technology. Perhaps wormholes would follow a similar path, from military or elite use to general public utility. Still, ensuring fair access would be a challenge, requiring conscious effort. Finally, consider the environmental and existential risks. Every wormhole manipulation is an interference with space-time structure. Could creating or using wormholes have unforeseen side effects, like triggering that vacuum decay scenario or disrupting orbits? Ethically, we'd need to weigh the potential harm of tearing space-time against the benefits. It might be akin to early atomic scientists worrying about setting the atmosphere on fire with a nuclear test, an extremely low probability event, but with annihilating consequences if it came true. Responsible science demands we assess these risks honestly. Perhaps initial wormhole experiments would be done far from Earth, in case something went awry, or on a small scale before scaling up. In summary, wormholes would demand a new ethical framework. We'd need a blend of caution, international cooperation, and forward-thinking regulation to use them wisely.
Much as the world came together, however imperfectly, to prevent nuclear war and to manage space resources peacefully, a similar or greater unity might be required to handle wormhole technology. The goal would be to maximize the wondrous benefits: quick travel, instantaneous communication, cultural exchange, while minimizing opportunities for disaster or domination. Achieving that balance could be one of humanity's greatest ethical tests, essentially asking, can we wield the power of the gods without succumbing to our very human flaws? Handled wisely, wormholes might even open pathways to domains utterly foreign to us. Among the wildest possibilities is the idea of connecting not just different regions of our universe, but entirely different universes. Across the multiverse, bridges to parallel realities. The word universe used to mean everything that exists. But modern cosmology and quantum theory have opened the door to the idea that our universe might be just one of many, a multiverse. If so, wormholes might not limit themselves to connecting points within one universe. They could, at least in theory, link different universes altogether. What do we mean by different universes? There are multiple concepts. One is the idea of separate bubble universes. Eternal inflation, a cosmological theory, suggests that as our universe inflated, other regions could inflate separately, creating bubble-like universes that are causally disconnected from ours. Normally, nothing can pass between bubble universes, but a wormhole might thread one bubble to another, like a tunnel between two separate soap bubbles. Another concept is brain worlds, which we touched on. Our universe could be a 3D brain floating in a higher dimensional space, and there might be other brains, other 3D worlds, parallel to ours in that higher dimension. Under the right circumstances, perhaps a wormhole is actually a tube through the higher dimensional bulk connecting two brains. If you stepped through, you'd literally leave our cosmos and emerge in a separate 3D universe with its own content. Yet another notion comes from quantum physics' many worlds interpretation, which posits that every quantum event that has multiple outcomes actually splits the universe into multiple branches, essentially parallel timelines or universes where each outcome occurs. Normally, those branches do not interact. They're like separate tracks of reality. But some speculative discussions wonder, could a wormhole allow travel between these quantum branches? This is a more exotic and controversial idea, but it's a staple of science fiction. The idea of alternate histories where, say, a wormhole could let you visit a world where the dinosaurs never went extinct, or where a different outcome of history occurred. If wormholes can connect parallel universes, the possibilities are as vast as the imagination. You could have a shortcut, not just to another galaxy, but to an entirely different reality with different initial conditions, maybe even different physical constants. Some theoretical physicists have played with models where a wormhole connects a universe that has, say, a different value of the electromagnetic force. Stepping through might mean entering a realm where atoms are of a different size, or stars burn at different rates. That sounds dangerous, and it would be, but it shows how far one can extend the mathematics. There is even a theory that black holes could be wormholes to new universes. One proposal is that when matter collapses into a black hole singularity, perhaps quantum gravity saves the day by avoiding an infinite crunch. Instead, the collapsing matter tunnels through a wormhole-like process and pops out as a new Big Bang in another universe. In this picture, every black hole might be an embryonic universe internally. If that were true, we don't know, then our universe's own Big Bang might have been born from the interior of a black hole in some parent universe. It's a mind-bending idea. Wormholes as the umbilical cords of baby universes. Now, have we any evidence of anything beyond our universe to even hint at wormholes connecting universes? Not really. By definition, other universes, if they exist, are not observable except by perhaps subtle gravitational effects, or if a wormhole gate exists. There have been claims of unexplained cold spots in the cosmic microwave background,
that some attributed to a collision with another universe's bubble. But those interpretations are speculative. If a wormhole connected to another universe, how would we know it's another universe and not just another part of our universe? One clue might be if something impossible appears through it, say stars or particles that don't match what our universe's physics allows. Perhaps the chemical composition is weird, or physical constants measured through the wormhole region seem off. If you stuck a probe partially through a wormhole and noticed that on the far side pi calculated differently, or the spectrum of hydrogen was shifted, you might suspect you're not in Kansas or this universe anymore. Why entertain such extreme ideas? In part because modern physics has extreme ideas on the table anyway. Multiple dimensions, many worlds, etc. Wormholes are already exotic, so connecting them to other exotic frameworks is natural for theoretical exploration. And philosophically, it's alluring. Wormholes as a tool, not just for spacefaring, but for multiverse exploration. Civilizations might not only spread across their own galaxy, but hop to entirely different universes, effectively making them inter-universal travelers. It's the ultimate frontier. From a story perspective, it raises stakes and puzzles. If wormholes can connect universes, then somewhere out there could be an alternate version of you, and a wormhole could bring you face to face. Or a universe where life never arose might be colonized via a wormhole by life from our universe. One could contemplate a network of wormholes linking a meta-universe of many worlds. Now, scientifically, this remains in the realm of speculation. We have no evidence of other universes, and wormholes themselves are unproven. So a wormhole connecting universes is speculation squared. But it's a healthy exercise in pushing limits. It forces us to clarify what we mean by universe and space-time. If nothing else, thinking about multiverse wormholes brings us back to the philosophical. What is reality? If wormholes let us step outside our known reality, does that change our perspective of our place in existence? Perhaps in confronting the multiverse, we realize how precious our particular home universe is, or conversely, how small it is in a larger ensemble. One practical consideration. If a wormhole can connect two universes, can it disconnect? If that wormhole closes while you're in another universe, you could be truly stranded, with no realm of existence to return to. The bravery, or folly, of stepping through a wormhole to an entirely different reality is immense. As we come to the end of our speculative trek, it's fitting to turn reflective. Wormholes, real or not, force us to re-examine our notions of distance, time, and separateness. They are a mirror to our desires and our fears. What would it mean for beings like us to have such power? What would it do to how we see distance, presence, causality? This leads us into the philosophical domain, reconsidering fundamentals like far and near, and reflecting on the human condition in light of these cosmic possibilities. Rethinking reality. Philosophical implications of wormholes. The mere possibility of wormholes compels us to re-examine some deeply held intuitions about space, time, and our own lives. Distance and space. We normally think of space as something that guarantees separation. If two cities are 1,000 miles apart, that distance is an obstacle. It implies travel time, effort, maybe the impossibility of daily interaction. On cosmic scales, distance becomes almost synonymous with isolation. Galaxies are millions of light years apart, effectively meaning we cannot interact within any human timescale. Wormholes, if they exist, break that notion. They suggest that distance is not an absolute barrier, but a malleable dimension that can, in principle, be folded or pierced. If you can step through a wormhole and be 1,000 light years away in a second, then far and near cease to have the same meaning. The emotional weight behind distance, the sense that loved ones are irretrievably far or that a place is out of reach, would be profoundly changed. Wormholes would make the universe, even the multiverse, feel that much smaller and more connected. This echoes, in a philosophical way, the idea from quantum entanglement
that maybe all points in space are secretly tied together. With wormholes, that would be literally true for the points they link. Presence and location. If wormholes allow essentially instantaneous relocation, what does it mean to be here or there? We might become entities that exist effectively in multiple places in short order. You could wake up on Earth, have lunch on a planet orbiting Vega, and be home by evening. Our sense of home might expand to include multiple worlds. Presence becomes a choice, not a fate determined by where you were born or where you currently stand. In a sense, wormholes could liberate us from geography. On a deeper level, it makes us ask, is location an inherent property or just a temporary condition? If you and I can meet physically despite living galaxies apart, then distance truly becomes a state of mind, almost an illusion broken by knowledge and technology. Consider also identity. Throughout history, communities have been shaped by who can physically meet whom. Wormholes would scramble that. You could form a community of beings from different star systems who meet daily in a common space via wormhole. This would challenge cultural and personal identities to broaden. Earth-based identifiers might seem trivial when your best friend is from a planet 50 light-years away. Philosophically, one might argue wormholes make us realize the triviality of physical distance in defining relationships or communities. Causality and time. Wormholes blur the clear arrow of time if used improperly. This forces a philosophical stance. Perhaps the universe has a strict rule, no going back and altering things, as Hawking humorously said, to protect the historians. Or perhaps the universe is okay with loops and multiple timelines. If wormholes allowed time travel, we'd confront the paradoxes we discussed not just as abstract, but as ethical and existential issues. Could you maintain a coherent sense of self if your personal timeline is no longer linear or unique? What becomes of responsibility and causality if effects can precede causes via a wormhole shortcut? Some philosophers suggest that if time travel, via wormholes or otherwise, were possible, free will might be an illusion, or the universe might be a block where everything is predetermined to avoid paradox. Or if multiple timelines are created, then every possible choice is made in some branch. Again, challenging the idea of personal responsibility or unique identity. You exist in countless variants. Even without time travel, wormholes shorten cause and effect delays. A supernova that would have taken 100,000 years to affect us via normal space, like sending a shockwave or cosmic rays, might, through a wormhole connection, affect us immediately. That entangles distant events with local ones in a way that upends our usual causal order. Cosmic events usually play out on timescales safely separate from human ones, but wormholes change that. Travel without moving. This phrase, popularized in fiction, like the spice navigators in dune-folding space, or mysticism, becomes almost literal. Wormholes allow one to go somewhere without the journey in between. Philosophically, journeys have been metaphors for personal growth. It's not the destination, it's the journey, people say. If the journey is instantaneous, do we lose something? One could worry that eliminating travel, the process, might cheapen the experience of reaching a destination. On the other hand, one could argue that we find meaning in what we experience, not how long it takes. Wormholes might force us to find new ways to gain the perspective and growth that travel over time and space used to provide. Perhaps with the drudgery of transit gone, we'd spend more time truly engaging with new places or peoples. It also raises Zen-like questions. There's a well-known koan, without moving, you arrive. Wormholes make that concrete. It challenges the primacy of physical movement in our conception of progress or adventure. You could cross the universe by taking a single step through a portal. It's very anti the classical heroic journey, which is full of trials. Does that make the universe less grand if it's so easily crossed? Or does it simply remove the barriers so we can focus on what truly matters, knowledge, connection? The unity of space-time. Einstein already unified space and time conceptually.
Wormholes, in a sense, unify separated spaces and potentially separated times. They bring far-flung corners into contact. Philosophically, this resonates with ideas of underlying unity, that all things are connected. Many spiritual traditions speak of oneness, that separateness is an illusion. Wormholes would be a literal manifestation of that principle. For certain points, the distance is zero. If one embraced that metaphor, you might say wormholes show us that the universe is deeply interconnected in ways our senses did not initially reveal. Perhaps what we perceive as empty space between objects is not a forbidding void, but something that can be bridged by understanding nature's hidden dimensions. Human meaning and purpose. Since time immemorial, part of the human condition has been coping with separation. From each other, distance, from places we care about, even from times, the past, future. We've invented telephones, airplanes, the internet to mitigate these, but wormholes would nearly eliminate them. What then? Some might fear a loss of challenge. If you can go anywhere or anywhen, what do you long for? Others might say it allows us to focus on higher goals now that basic separation is solved. It also touches the existential longing. Are we alone? Wormholes, if they allowed meeting aliens easily, could fill the universe with neighbors. But then, the specialness of Earth might diminish, or we might feel less unique, which is both humbling and potentially troubling if we define ourselves by our uniqueness. Ultimately, wormholes bring to life the phrase, annihilation of space and time, something early telegraph users in the 19th century marveled at when messages could outpace horses. With each leap, trains, planes, radio, internet, we've had to adjust our philosophical and societal outlook. Wormholes would be a leap orders of magnitude greater. It would force a kind of cosmic cosmopolitanism. The Earth could be as connected to a planet in Andromeda as New York is to London today. The psychological impact could be huge, perhaps expanding our empathy to truly cosmic scales, or causing a kind of culture shock as humanity, or any species, faces a radically enlarged scope of life. One can also ponder, if wormholes allow us to be effectively everywhere, do concepts like frontier or exploration lose meaning? Part of our drive comes from things being difficult to reach. If everything is reachable, do we become complacent? Or do we find new frontiers in realms of knowledge, art, internal consciousness? Probably the latter. We shift from physical exploration to exploration of ideas or creativity. The external frontier might become the internal frontier. In embracing wormholes, we would be taking on what once were attributes of gods: omnipresence, being anywhere quickly, and perhaps even some form of immortality or time manipulation. Philosophers and theologians might have much to say about humans stepping into those shoes. Is it hubris or fulfillment of destiny? Are we playing God by rearranging space-time, or are we simply utilizing the tools the universe gave us? As we reel from these profound thoughts, it's clear that wormholes, whether real or not, function as a splendid mirror. In them, we see reflected our eternal desire to not be bound by limits, not by distance, not by time, not by isolation. They encapsulate our refusal to accept that the stars are beyond reach or that the past is forever gone. Wormholes are, in a way, the scientific analogue of hope and imagination, an insistence that somewhere, somehow, there must be a way. And so we come full circle to the human heart of this matter. Why do we yearn for wormholes? Because, at root, they represent connection, the defeat of cosmic loneliness. It's fitting then to conclude by returning to that emotional core, reflecting on how, through love, curiosity, and indomitable will, we strive to forge connections that even space-time cannot tear apart. Beyond all distance, the human drive to connect. From the moment early humans first climbed a hill and wondered what lay beyond the horizon, we have been a species of explorers and bridge builders. We crossed oceans with fragile ships, traversed continents on foot and horseback, and eventually soared through the skies in airplanes. Each time we encountered a horizon,
we found a way to reach beyond it. The greatest horizon of all has been the sky above, the vastness of space and time. Wormholes represent the ultimate bridge, the final answer to the challenge of distance. Why do we care so much about bridging distance? It's not just curiosity, though that is a powerful engine. It's also something profoundly emotional. We seek to not be alone. We yearn to connect with others, to see and touch the places that inspire us, to ensure that nothing, not even light years of emptiness, can keep us apart from what we love or desire to know. Think of the loneliness of a spacecraft drifting between stars, decades from any signal. Now imagine that isolation erased by a shortcut. A crew steps through a wormhole and instantly finds themselves greeted by the light of a new sun and the faces of colleagues who went ahead. That moment would be transformative, a triumph over what once seemed an iron law of nature. It would say, we refuse to accept separation. Throughout this script, we've danced between cold equations and poetic visions because wormholes demand both. The science might one day allow or disallow them, but until then, they live in our collective imagination as symbols of ultimate possibility. They whisper that maybe, just maybe, the universe is kinder than it looks, that the great distances that keep us apart might be circumvented by intelligence and perseverance. Consider a future where wormholes are real. A grandmother on Earth could hug her granddaughter on a colony light years away and be home by evening. Scholars could walk through a library wormhole to consult archives on a planet in another galaxy. Friends separated by time could, through the careful use of a wormhole, meet again at a chosen moment. These are almost utopian scenarios, of closeness regained, of knowledge unbounded. And yet they spring from the same fundamental human motivation that sent explorers across uncharted seas and astronauts to the moon. The desire to reach, to connect, to understand. In a sense, wormholes, real or not, hold a mirror to humanity. They show that we are not content with walls and limits. If space has an end, we want to see what lies beyond. If there's a barrier, we feel an urge to bridge it. This refusal to be confined, this restless drive, is one of our defining qualities. It is the reason people first left their home valleys, the reason we send robotic emissaries beyond our solar system, and the reason we contemplate technologies as extreme as wormholes. Of course, any technology is double-edged. Control of wormholes would be an immense power. Who decides how they're used? Could they be weaponized? We touched on how it would require great wisdom and cooperation to use such power safely. But let's imagine that we rise to the occasion. That knowledge is guided by compassion and caution. In that case, wormholes could become arteries of empathy as much as commerce. Imagine not just exchanging goods, but ideas and cultures freely across light years. The galaxy, or galaxies, could become a tapestry of interwoven civilizations, each unique but connected. There's a poignant aspect too. If one day we master wormholes, what next? Will there come a time when every point in space we care about is accessible, and we'll look outward and find no place new to go? Perhaps then we'll turn inward, to the infinite spaces of mind and creativity, frontiers that can never be exhausted. Perhaps wormholes, by solving the external challenges of distance, will let us focus on exploring questions of meaning, purpose, and inner fulfillment. As we reach for these keys to the cosmos, we find ourselves living out the oldest dreams of our species. We have always imagined magic portals and celestial bridges, from the rainbow path of Norse myth to the flying chariots of Hindu lore, ways to connect realms separated by vastness. With wormholes, those age-old fantasies inch toward reality, rendered in equations and engineered apparatus. The line between myth and science blurs. We become, in a sense, the bridge builders that our ancestors could only ascribe to gods, opening the gates of heaven, uniting worlds, transcending limits. These powers move from folklore to the laboratory. The challenge is,
are monumental, but so is our collective will to overcome distance. In pursuing wormholes, we are propelled by the same force that once made us launch ships across uncharted oceans and send signals into the dark of space, the unyielding human spirit of connection. It is that spirit that will light our way as we strive to unlock nature's most wondrous back doors and step through into whatever lies beyond. The cosmos awaits. Perhaps not as a void to be feared, but as a home rich with rooms and hallways we have yet to walk. Our longing to traverse its depths is, in the end, a longing to fulfill our own potential. Wormholes or not, that spirit of connection will continue to guide us as we live out this grand story written in the stars, forging bonds that even the fabric of space-time cannot sever. As we reach for these cosmic doorways, we are echoing our oldest tales of secret passages to the heavens. But this time, we might hold the key in our hands. We find that the bridges we seek out there have been inspired by what is in here all along, our capacity to wonder, to strive, and to connect. For generations, we've told stories of magic portals and divine chariots bridging worlds. With wormholes, those narratives edge toward reality under the guidance of science. In building these gateways, we step into roles once reserved for the gods in our legends, opening celestial doors, uniting what was separate. And though the technical challenges are immense, our drive to connect is even greater. It will be the light that guides us through those cosmic doorways. In the end, the pursuit of wormholes is not just a scientific adventure, it's a celebration of the human spirit. It shows our refusal to be limited by distance, time, or even reality itself. Whether or not wormholes become a practical reality, the hope and determination behind them will continue to define us. We will carry with us all the dreams of those who dared to believe that no door stays closed forever. A lone observer gazes up at the night sky, heart heavy with the weight of distance. The stars glimmer like distant lanterns, separated from us by unfathomable oceans of space. In that vast darkness between worlds lies an almost impossible gulf, a silence, a void that seems to forbid crossing. How can something as small as a human mind even conceive of bridging such an expanse? And yet, we do. We always have. In our stories and dreams, we rebel against distance. We imagine secret doorways and hidden roads that might collapse the chasm between here and there. For as long as we've felt the ache of separation, we've yearned for a bridge to connect the far-flung corners of the cosmos. Distance defines our reality. Light itself, the fastest thing we know, takes years to traverse the space to even the nearest neighboring star. We measure those spans in the lifetimes of civilizations. It seems the universe has erected an iron law. Nothing can travel faster than light, and so nothing can easily overcome the emptiness between the stars. And yet, when we yearn to explore, when we long to not be alone in the cosmos, that law feels like a cage. The soul of every explorer, every lover of starlight whispers, must it be so? Must the void remain unbridged? In the quiet of midnight, under the canopy of endless stars, we dare to hope the answer is no. The human heart rebels against the tyranny of distance. We tell tales of miraculous voyages that cheat the miles. We close our eyes and imagine, what if, somewhere in that darkness, a hidden tunnel could take us from one end of space to another in a heartbeat? What if the farthest reaches could be closer than they appear? The thought is intoxicating, a balm for the deep loneliness that sometimes accompanies our view into the infinite. In that emotional landscape, the idea of a wormhole, a shortcut through space and time, is born not just from mathematics, but from longing. It arises from the need to connect, to make the unreachable reachable. So our story begins with a feeling, a nearly primal desire to defy separation. Before any theory or equation, there was this yearning across the cosmic gulf,
This dream that the impossible distance might not be final. It is a dream as old as humanity, woven into our earliest myths. The desire for a bridge through the void is the seed, and from that seed will sprout one of the most astonishing ideas in science, the wormhole, a tunnel through space-time itself. But before science gave it a name, imagination paved the way. The cosmos above, cold and silent, stirred something warm and rebellious in our hearts. We begin with that warmth, that defiance, an emotional overture to a journey that will span ancient myth and cutting-edge physics, carrying us through shadows and wonders, all centered on one tantalizing possibility, that perhaps no distance is truly unbridgeable. Bridges of myth and memory. Long before we had equations or observatories, we had stories. In the deep well of history, when our ancestors looked at the night sky with wonder and fear, they crafted myths to make sense of the heavens. And in those myths, they often imagined bridges between worlds. Perhaps in a world lit only by fire, the notion of an actual journey to the stars was beyond comprehension, but the heart still yearned to travel, so they built their bridges in myth and memory. There is an ancient story of a shimmering rainbow bridge arcing up from the earthly realm to the realm of the gods. In the tale, this radiant archway, born of storm and sun, was the cosmic highway that heroes and deities could tread. In another tradition, a prophet dreams of a ladder reaching to the sky, with angels ascending and descending, a promise that earth and heaven are not so hopelessly sundered after all. And across cultures, the idea resurfaces in countless forms. A world tree with roots in our world and branches in the next, binding together the domains of mortals and gods. Sacred mountains touching the sky, serving as pillars that travelers might climb to reach the divine. These myths whisper that the divide between here and beyond can be crossed with the right path. By the flicker of ancient fires, people told of secret roads through the firmament, of chariots that carried souls to the heavens. Every tale was a reflection of the same inner conviction, or perhaps longing, that the separation between distant realms is not absolute. They imagined tunnels of light, ropes of wind, ladders of stars. It was as if human imagination, unable to accept isolation in an infinite cosmos, painted over the void with stories of connection. These were more than mere flights of fancy. They were expressions of a deep need to belong to a larger universe, to have a way to reach it. In these mythic bridges, we see early shades of the wormhole idea. Not in detail, of course, but in spirit. A wormhole is, at its heart, the ultimate bridge, a literal tunnel through the fabric of reality. The ancients didn't speak of space-time or geometry. They spoke in the language of symbol and dream. A rainbow that you could walk across to the far side of the sky. A magical tunnel where a hero enters a cave on one side of the world and emerges in a far-off land or a different plane of existence. Every culture seems to carry a version of this archetype, the shortcut, the portal, the secret door. Why such universality? Perhaps because to be human is to often feel separated from knowledge, from gods, from other worlds, and to yearn for unity. The cosmos, with its unreachable stars, was the greatest separation of all. So our ancestors filled it with bridges of meaning. The axis mundi, the world axis, was said to connect earth and sky, a cosmic spine joining all realms. Even in ritual and architecture, towering spires, sacred pyramids, we mimicked the idea of ascending toward the heavens. It's as though something in us has always rebelled against walls and distances. We create paths where none can be seen. These ancient bridges were metaphorical wormholes of a kind, born from emotion and imagination rather than physics. They could be traversed by spirits or chosen heroes rather than spaceships. But they primed humanity's collective mind for the idea that would come much later, that maybe the universe itself has hidden pathways.
The old myths gave us permission to believe that extraordinary shortcuts might exist. They kept alive the flame of hope that there is a way to cheat the abyss. As time flowed on and civilization advanced, that hope would find new expression. Myth would give way to mathematics. The rainbow bridge would transmute into a calculation on a physicist's blackboard. But it's important to remember that before wormholes were equations, they were dreams. The mythic ladders and bridges were humanity's first draft of the wormhole story, written in the ink of wonder and longing. They led us, step by step, to a point where we could ask, in the language of science, could such a bridge be real? Could nature allow it? Thus, ancient myths set the stage. They handed down a timeless narrative of connection across cosmic separation. All that was needed was for someone, millennia later, to reimagine that narrative in terms of space, time, and gravity. The desire for a cosmic bridge was waiting, latent in our cultural memory, like a seed beneath the snow. It would only take the light of modern insight to make it bloom into the concept of the wormhole. A bridge in the equations. Fast forward to a little over a century ago. The age of myth had long since given way to the age of reason. We had begun to decode nature's secrets with experiment and calculus, and one man's revolutionary vision had reshaped how we see space and time themselves. It was in the early 20th century that the geometry of the universe was revealed as something dynamic and alive. Space and time were no mere backdrop. They could bend, rippling like a fabric under the influence of matter and energy. This was the essence of the new theory, a theory that would eventually hint at wormholes lurking within its mathematics. The theory was general relativity, the brainchild of a quiet patent clerk turned titan of physics. It gave us equations, beautiful, complex equations, describing how gravity is not a force that pulls at a distance, but rather the very shape of space-time curving around mass. Planets orbit stars not because of invisible pull, but because space itself is warped by the star, guiding the planet's path. It was a radical, elegant picture. Matter tells space-time how to curve, and space-time tells matter how to move. In these equations, space and time were woven together into one fabric. And like any fabric, this cosmic tapestry could have odd contours or holes. A handful of brilliant thinkers explored those equations deeply, seeking strange and exotic solutions like explorers venturing into a mathematical jungle. And lo, in that dense thicket of symbols, they found something remarkable: a bridge. It appeared as a mere quirk of the math at first, an implication that under certain conditions, space-time could connect two regions that would otherwise be separate. This connection looked, in the equations, like a tunnel, a throat linking one universe or location with another. The find was so surprising that even its discoverers weren't entirely sure what to make of it. Imagine deriving on paper that space might allow a shortcut. It was as fantastical as the myths, yet born from rigorous logic. This hypothetical tunnel came to be known as an Einstein-Rosen bridge, named after two of the minds who described it. In their calculations, they were examining the gravity of a collapsed star, what we now know as a black hole. They realized that mathematically, the interior of such a gravitational pit could be extended, mirrored, forming a kind of back-to-back funnel shape. Picture two bowls whose rims are glued together. Stuff could fall down one bowl and potentially pop up the other, if the tunnel connecting them stayed open. To make a mental image, envision space as a stretchy rubber sheet. Place two heavy balls, representing massive stars, far apart on the sheet. Each dents the sheet into a deep well. Now imagine pushing the bottoms of those wells toward each other from beneath until they meet and fuse. You'd get a tunnel connecting the two surface dents, a bridge from one location on the sheet to the other. On paper, the equations permitted this weird topology. Suddenly, the concept of a tunnel through space was no longer confined to mystic legend. It had a foothold in real physics, albeit a theoretical one. The initial hope, at least for the scientists playing with these equations, was not about interstellar travel, interestingly. They were struggling with an annoying problem. The equations of gravity seemed to break down at that point of infinite density at a black hole's center, the dreaded singularity. To avoid that, the solution they found effectively removed the singular point and replaced it with a pathway to another patch of space. In doing so, they inadvertently described a wormhole. They were trying to mend the fabric to avoid an infinite tear, and they found a tunnel connecting two universes as a byproduct. It's as if, trying to avoid a dead end in a maze, they punched a hole in a wall and discovered an entirely new corridor. News of this peculiar solution, this Einstein-Rosen bridge, spread quietly among physicists. At first, it was a mathematical curiosity, more than a serious proposal for cosmic travel. But the seed was planted. The ancient dream of a cosmic passage had been reborn in the dry language of differential geometry. The bridge was fleeting in that first incarnation. It seemed to exist only in a timeless sense, or for an instant before collapsing. But still, it was there. Equations etched on a page had become a modern scripture, revealing the possibility of connecting distant places. One can imagine those scientists, late at night in lamplight, marveling at what they had written. Did they feel a thrill of the mythic? Did they recognize the echo of the old rainbow bridges and sky ladders in their findings? Perhaps not overtly. They were men of reason, after all. But on some level, the discovery must have stirred a sense of wonder. The universe, through the prism of gravitation theory, had whispered a secret. I contain paths unseen. And so the concept of the wormhole entered scientific consciousness, quietly, almost shyly, as a side effect of gravity's equations. A bridge in math, waiting to be interpreted. It would take years, even decades, for others to fully grasp its implications, to ask the bold question, could this be real? Could something or someone actually travel through such a bridge? What would it take to keep it open? For now, in our story, we have reached a pivotal moment. The birth of the wormhole concept in scientific thought. Myth has met math. The cosmic ladder has become a tunnel in space-time's geometry. It's fragile and strange, but undeniable within the logic of the theory. A door has cracked open, theoretically, in the wall of impossibility. Through that crack we glimpse an extraordinary road that could, in principle, lead across the light years in a single step. The stage is set for the next chapter, figuring out what exactly a wormhole is and whether the universe would allow one to last long enough for a daring traveler to step through. Two mouths and one throat. So, what exactly is a wormhole? We have used words like tunnel, bridge, shortcut, but let's paint a clearer picture, one we can hold in the mind's eye. To do that, we'll use a bit of metaphor, because a wormhole is not something we can photograph or hold in our hands. Yet with imagination, we can sketch its outline. Picture space as something like an immense fabric or an endless landscape. Normally, if you want to get from point A to point B on this landscape, you must traverse the ground between, every inch of it. But suppose there's a secret tunnel underground that opens at A and emerges at B. If you step into that tunnel, you vanish from the surface and pop out at B without having to walk the distance on the surface. That is the essence of a wormhole. It connects 2 points in space-time that would otherwise be separate, providing a shortcut through a higher dimension. In physical terms, a wormhole has 2 mouths and 1 throat. The mouths are the entry and exit points. Think of them as 2 doors or portals, perhaps many light years apart, or conceivably in different universes entirely, but somehow linked. The throat is the tunnel or conduit between those mouths, the space within the wormhole itself through which one would travel. If you were an intrepid voyager, you would dive into one mouth, journey through the throat, and emerge out of the other mouth, finding yourself in a place that might be unbelievably distant from where you started.
yet the trip could have taken only moments. One way to imagine it is to take a sheet of paper and draw two X's far apart, representing two stars or galaxies. In normal reality, the line between those X's is long. That's the arduous path a beam of light would take, which might be thousands of years long. Now fold the paper so that the two X's align on top of each other. Jab a pencil through that spot. The hole you punctured is the wormhole. It touches both X's at once because of the folded higher dimension. Of course, in reality we can't just fold space with our hands, but space-time can curve and connect in ways our Euclidean intuition finds surprising. The wormhole effectively brings those two far-off points together in a higher dimensional sense, even though in regular 3D distance they remain far apart. Inside the wormhole, the usual rules of here and there begin to blur. We might poetically say, inside the throat, here and there dissolve into one. The interior of a wormhole is not a place we can easily map. It's like being in a corridor that itself is outside the usual space. You might travel a few meters through the throat and exit tens of trillions of kilometers away from your start. The distance inside the wormhole is not the same as the distance outside. It's as if the cosmos has a hidden network of secret passages behind the walls of the observable world. The term wormhole itself conjures a humble analogy. Think of a worm burrowing through an apple. To the worm, the apple's flesh is like the fabric of space. If the worm bores a tunnel, it can pop out at a distant surface point without crawling around the apple's surface. In the same way, a space-time wormhole is like a tunnel through the apple of the universe, a hole that bypasses the surface route we normally must take. It's important to realize a wormhole isn't a rip or tear. It's more like a gentle curve and connection. Space is still continuous around it, but the wormhole offers a kind of detour that wasn't apparent in the flat map. If you stand outside a wormhole mouth, it might look like a sphere or circle, depending on the dimension, that is essentially a portal. Peering into it, you wouldn't see the back of the cave you might expect. You'd see what lies at the far end of the wormhole. It could be another galaxy's starscapes, shining out of that strange spherical doorway floating in space. Imagine drifting in the quiet void between stars and coming upon a shimmering, spherical mirror hanging in darkness. As you draw near, instead of your own reflection, you see an alien sky on the other side, perhaps the swirls of a distant nebula or the light of a far-off sun. Walk around this sphere, and from every angle, you see the same otherworldly vista within it. Stick your hand through, and your hand vanishes into some remote corner of the cosmos. That's a fanciful yet apt visualization of a wormhole mouth. It's a window and a doorway all at once, its edges perhaps ringed with gravitational lensing effects that make starlight curve strangely around it. The throat connecting the two mouths could be relatively short or tremendously long. It's a hyperspace tunnel invisible to the outside universe. To anyone not using the wormhole, nothing can travel faster than light, and the two mouths might be light years apart. But to someone who steps inside, the separation is an illusion. The throat provides the superluminal shortcut. In essence, a wormhole is a place where the normal rules of distance are suspended. Here and there, before and after, these distinctions get fuzzy. Entering a wormhole, you leave behind the conventional map of reality and move in a kind of higher-order space. It's a bit like a maze behind the mirror of the world, an unseen labyrinth that occasionally lets out at unexpected locations. This concept, while born from sober mathematics, is so fantastic in its implications that it demands metaphor. We say two mouths, as if some great cosmic creature were gaping in two places, with a throat joining its gullets. We say bridge, as if engineers could bolt one end of space to another like girders. These analogies strain comprehension, because nothing in everyday life truly matches a wormhole. And yet, these metaphors spark our intuition and guide us. So, to summarize our mental model, a wormhole is a tunnel through space-time. It has two ends, mouths, and a tube-like interior. throat. Step through one mouth, emerge from the other. The travel time through the throat can be arbitrarily small compared to the distance you circumvent outside. It's as if the universe had secret teleportation gates built into its very geometry, but they are tunnels, not magic teleporters, meaning you actually traverse a path, just one hidden from normal view. Hold that picture in your mind. The two mouths, one throat, the dissolving of here and there. It is the foundation for everything that comes next. Because while this idea is beautiful, nature is not so easily tamed. The equations showed a possible bridge, yes, but they also hinted that this bridge might be perilous or even illusory. What keeps the tunnel open? If gravity is warping space enough to create a wormhole, gravity might also want to slam it shut. In fact, the earliest indications were that such a wormhole would collapse before anything could pass through, a tantalizing door that always slams closed too quickly. To walk these hidden corridors of the cosmos, we might need something extraordinary to prop them open. And that leads us to one of the strangest concepts in physics, matter that behaves in ways no ordinary matter does. The next act in our journey, we seek the key to holding a wormhole ajar. The exotic thread that binds. Our theoretical wormhole, as originally conceived, is ephemeral, a mayfly of a structure, appearing and vanishing almost instantaneously. Under the immense gravitational stresses that form it, the throat of the wormhole wants to pinch off. It's like a fragile tunnel made of sand that immediately collapses under its own weight. To keep it open, we'd need something truly outlandish, something that pushes back against gravity's relentless crush. Enter the idea of exotic matter and negative energy, the bizarre thread that might bind a wormhole and prevent it from collapsing. What do these terms mean? In our everyday experience, matter always exerts gravity, always pulls. Energy, like the light from a star or the heat from a fire, has mass equivalence and also tends to gravitate normally. But the equations of physics tantalizingly allow for the existence of forms of matter or energy that are, in a sense, the opposite. They would repel rather than attract. They would have what's called negative energy density, meaning their presence could make space stretch outward rather than curving inward. This is not stuff we encounter in daily life. You can't scoop a handful of negative energy from a jar. But quantum physics tells us that, under special conditions, the energy of empty space can be lower than usual, effectively negative relative to normal. It sounds like pure sorcery, matter with weight that lifts instead of sinks, energy that has a sort of anti-gravity effect. But quantum theory gives us a concrete example in the form of the Casimir effect. Place two mirrors extremely close together in a vacuum. Quantum fluctuations, the ghostly particles that flicker in and out of existence even in emptiness, behave differently between the mirrors than outside. The result is that between the plates, the energy density is actually lower than in normal empty space. It's as though we tricked the vacuum into having less than nothing. This is a measurable, if tiny, negative energy. Now, scientists speculated. If negative energy exists in principle, perhaps one could accumulate enough of it, or a form of exotic matter that has negative mass energy, to stabilize a wormhole. The idea is to line the throat of the wormhole with this exotic stuff. Like rivets and steel beams propping a tunnel, this negative energy would push outward against the wormhole's walls, preventing gravity from crushing it shut. Gravity wants to collapse the throat. Exotic matter says, no, stay open. In a classic analysis, physicists found that a traversable wormhole, one you could actually travel through without it collapsing, would indeed require such exotic materials. Ordinary matter won't suffice. Drop even a single pebble into a delicately balanced wormhole, and its mass would tend to make the hole implode. But if the wormhole's throat were threaded with something that has negative gravity, it could hold open against that collapse. It's akin to having walls of a tunnel made of some pressure that counters the natural tendency to cave in.
This requirement makes wormholes seem even more fantastical. We not only need a tunnel through space-time, but we must also conjure up a substance that by all rights shouldn't exist in bulk. And yet, our theories do not forbid negative energy outright. They merely constrain it. Quantum fields can produce it in small regions for short times. The big question becomes, could nature produce enough exotic stuff to stabilize a macroscopic wormhole? Or could an immensely advanced civilization somehow farm or engineer quantum effects to gather negative energy? Imagine a future lab where scientists, perhaps millennia ahead of us, manage to collect vacuum fluctuations like someone bottling lightning. Bit by bit, they amass an ocean of ghostly energy with the curious property of being less than nothing. This negative energy might be held in some energetic cage or electromagnetic bottle. To create a wormhole, they might somehow apply this to a region of space, warping it violently until a tunnel forms, then lining the tunnel with the negative energy to shore it up. It is a cosmic engineering task beyond anything we can truly fathom, but it's a theoretical blueprint for traversable wormholes. Another way exotic matter could appear is via strong electric or magnetic fields. In certain solutions of the equations, a very high electric charge can effectively contribute negative pressure. The early wormhole thinkers even mused about using electrical tension. What if we take two immensely charged spheres of the same charge and place one at each mouth? They would repel each other electrically, which might counteract the attractive collapse. If balanced just right, the tension could keep the throat from pinching. It's like using the stress in a stretch rubber band to hold open a pinhole. All of this sounds precarious and speculative, and it is. We have never seen exotic matter in large amounts. We've never made a traversable wormhole on any scale, even microscopic. But the math beckons that it's not outright impossible. The wormhole is a door barred by gravity. Negative energy is the hypothetical key. It's the toll or price the universe seems to demand for cheating locality. You must supply something that violates the usual energy conditions. This requirement also gave some physicists pause. It was almost as if the universe were trying to enforce a rule. Thou shalt not have an easy shortcut, by making the conditions to do so extremely stringent. Exotic matter might not be outright forbidden, but acquiring it in useful quantities could be practically unachievable. Perhaps only nature, under extreme circumstances, like quantum foam of space-time itself, could fleetingly produce such tunnels spontaneously. But to keep one open long enough for a person or spaceship to pass may require a miracle of physics. Nonetheless, it's a tantalizing thought. Somewhere out there, maybe near a ravenous black hole or in the early universe, pockets of negative energy might exist, holding a tiny wormhole open for a heartbeat before letting it collapse again. Or perhaps advanced beings, in the deep future or elsewhere in the galaxy, have mastered this exotic technology, pinning open wormholes like sewing needles pinning fabric. Through these artificially stabilized throats they might step, crossing distances in moments that light would take eons to traverse. One could poetically describe exotic matter as light woven from shadows, or an elixir of nothingness. It's the sort of thing that feels at home in a fantasy novel, yet it arises naturally from our quantum theories. Reality, it turns out, has its own form of magic, the quantum, which is weird enough to provide a hint of what's needed. So now our wormhole is conceptually complete, a tunnel through space-time propped open by a lining of exotic matter or negative energy. It's the ultimate archway, sturdy in defiance of collapse, allowing safe passage. Safe, at least, structurally. But what would a trip through such a passage actually feel like? Before we imagine daring heroes and starships boldly going through a wormhole, let's step into that scenario ourselves in our mind's journey. We have our wormhole stabilized by the strange physics we've mustered. Now let's dare to walk into the throat and see what awaits on the other side. Through the looking glass of stars. Consider, for a moment, that you are standing at the threshold of a wormhole, a traversable wormhole held open by whatever ingenious means. What lies before you is nothing short of a cosmic threshold, a doorway in space shimmering with possibilities. You take a deep breath, perhaps in a pressurized suit if this is truly in deep space, and you step forward, crossing into the mouth. What is it like? The first sensation might be the intense pull of gravity at the mouth, depending on how massive it is. But a traversable wormhole might be engineered to minimize tidal forces, the stretching and squeezing that intense gravity usually causes. Ideally, you feel a gentle tug, as if walking down a slight slope. The walls of the tunnel around you might glow with bent starlight. Remember, light can enter the wormhole too, so you might see light from the destination realm mingling with light from the origin. The throat could be suffused in an eerie radiance, like the inside of a deep ocean cave where sunlight filters in from both ends. Perhaps you notice that time itself feels strange. It's not something easily perceived, but clocks behave oddly near strong gravity. Yet, in a perfectly designed wormhole, time might flow smoothly for you as a traveler, while outside eons could pass, or maybe not, depending on how the mouths move relative to each other. We will touch on these paradoxes soon, but inside the wormhole, you're focused on the visceral experience. The tunnel might curve, not in the normal sense, but in how it connects one universe's coordinates to another's. You might look over your shoulder and still see the entrance where you came, perhaps the starfield of your origin world, and ahead, a pinprick of light that is the exit. As you venture deeper, space might feel compressed around you. If the wormhole throat is short, you traverse it in seconds. The idea of distance loses meaning. You take a few steps and cross unimaginable spans. If someone could watch you from outside, impossible since the interior is hidden, they might see you simply vanish. But for you, there is a journey, brief, wondrous, and perhaps a bit disorienting. Visualize walking through a tunnel where the walls are not rock, but the fabric of space itself, displaying swirling patterns of galaxies. It might resemble walking through a hall of mirrors, except each mirror doesn't show your reflection. It shows a distorted view of faraway nebulae and star clusters, smeared into arcs and rings by gravitational lensing. At one moment, you might see your destination ahead growing larger and more real. Perhaps you catch a glimpse of a planet or a sun that lies on the other side, like a circular window at the end of a hallway, growing from a dot to a doorway of its own. What about gravity inside the tunnel? It could be peculiar. If the wormhole is symmetric, you might feel gravity pulling you towards the middle from both ends, meaning it might feel zero at the very center. Or if one end is different, you might be gently pulled in one direction. This could be manageable, nothing like the deadly gradients near a black hole's singularity, since a traversable wormhole by design avoids those. So you likely won't be stretched into spaghetti or crushed. The experience is more akin to an amusement park ride through a cosmic funhouse. There might be a sensation of rotation or skew, as if space twists. Some wormhole solutions involve rotation or charge that can induce swirling effects on space-time. Imagine a slight corkscrew feeling as you move through, though it need not be violent. Think of gliding along a current in a calm river that just happens to be flowing through all of reality. Time for you could be only a blink. You step in, 1, 2, 3 steps, and you're out. But those few steps might correspond to light years of travel. It's as though you stepped behind a curtain in one city, and in 3 paces, emerged from behind a curtain in another continent. The transition might be subtle or dramatic. Perhaps a flash of light announces that you've exited. Or maybe it's incredibly smooth. One moment the tunnel walls are around you, next they dissolve and you're under an alien sky. What do you feel emotionally? Likely an overwhelming awe. One second you recall the stars as seen from your home. The next you see an entirely different constellation above. Perhaps a gigantic foreign moon looms on the horizon if you emerge near a planet. The air, if any, smells different. The color of the sunlight has changed, having come from a different star. You step out and realize you have crossed a practically uncrossable distance as simply as walking through a door.
Your body might feel a bit lightheaded. After all, even a perfectly designed wormhole might induce minor tidal effects that rock your inner ear. But physically, you are intact. If you had a watch and a friend back home had a synchronized watch, you might find, depending on how the wormhole moved, that not exactly the same amount of time has passed for both of you. Perhaps you are a few minutes younger than your friend now, a twist of time that came free with your journey. Passing through a wormhole could also have peculiar optical effects. As you approach the exit mouth, you might see multiple images of the outside world, as light can take multiple paths through the curved space and interfere. It could look like walking toward a shimmering pool of mercury that gradually clarifies into a normal view. Step out, and behind you, see not the tunnel you walked, but the mouth now behind you. Turn around, and you might see the universe you originated from, framed in the spherical gateway. It might appear as a strange glowing orb hanging there. If you wave your hand toward it, a distant friend on the other side might see a ghostly hand appear out of thin space at their wormhole mouth, waving back. It is, in a word, surreal. This is not a gentle stroll down a country lane. It's more like an acid trip through space-time. Reality warps, then reasserts itself differently. But for all the odd sensations, you have done the unimaginable. You've traversed a cosmic shortcut. Now, all this assumes a stable, benign wormhole. There are cautionary possibilities too. If the wormhole were to become unstable during passage, one might see the throat start to narrow, lights stretching into red as the passage contracts. That would be a race against collapse. A nightmare scenario where you might be crushed or severed if the tunnel pinches shut while you're mid-transit. But let's assume our engineered exotic support holds firm. Still, it would be hard not to feel a primal fear mixed with excitement. This is a journey inherently on the edge of what's known and safe. For a more everyday reference, perhaps the nearest analogy would be stepping into a dark cave, not knowing if the other end comes out on the surface or drops into a chasm. But here, the other end is another universe or galaxy. Crossing through a wormhole might also invite philosophical reflections in the moment. Inside that tunnel, usual reality falls away. You are in a space that doesn't belong entirely to either side. It might feel like a liminal space, a threshold where the normal rules and reference points vanish. Some travelers might describe a sense of unity or transcendence, as if they briefly walked in a realm beyond ordinary existence. Others might simply be focused on the mission, get to the other side. When you do emerge, it might be abrupt. One step you're enveloped in the twilight of the wormhole interior. The next, you're blinking in the bright light of another star system. Perhaps a new planet's gravity asserts itself under your feet. You have arrived, and turning back, you see the mouth behind you, possibly kept open so you can return. It might appear as a glowing orb or a black sphere rimmed in a halo. If you peer into it from this side, you'd see the place you left, now distant in the cosmos, but reachable through that doorway. The journey through a wormhole is as close to magic as physics might allow. It takes all the strangeness of relativity and quantum and wraps it into a single experience. It is inherently mind-bending because our intuition evolved trudging along surfaces, not jumping through spatial topologies. But at its core, if the wormhole is gentle, it might feel surprisingly ordinary. A few steps in a mysterious cave and out into a new world. The extraordinariness is in where you end up and how quickly, rather than in some violent ride. The calmness of such a passage, however, belies the deep, troubling questions it raises. For if you can traverse space so freely, can you also traverse time? Could a wormhole be not just a bridge in space, but in time itself? The answer from the equations is unsettling. Yes, potentially, wormholes could be time machines. And now that we've imagined a journey through space, we must confront what happens when that journey messes with cause and effect. The wormhole might not only take you elsewhere, it might take you elsewhen. And that opens a Pandora's box of paradox. The paradox of time's tunnels. Traveling through space via a wormhole is mind-blowing enough. But the wormhole's trickery doesn't necessarily stop at spatial separation. It can intertwine with time in the most baffling way. Imagine stepping into a wormhole today and coming out years in the past or the future. It sounds like science fiction piled atop science fiction, yet wormholes in theory make this not just possible, but perhaps inevitable under certain circumstances. These are the famous time travel paradoxes that wormholes provoke, and they challenge our understanding of causality, the chain of cause and effect that gives time its arrow. How could a wormhole allow time travel? The concept hinges on relativity's flexibility with time. Suppose you have a wormhole with two mouths, A and B. Now, if one mouth stays put and the other is whisked away on a high-speed journey, perhaps mounted on a fast spaceship, and then brought back, something intriguing happens. Relativity tells us that a clock moving at near light speed, or lingering deep in a gravity well, will tick slower relative to a stationary clock, a phenomenon called time dilation. So, the moving wormhole mouth B might come back younger than mouth A. That means the time inside B is behind the time at A. They are no longer synchronized. Now connect this thought. If you enter the younger mouth, B, and travel to the older mouth, A, you could pop out before you entered in terms of external chronology. For example, mouth A might be, say, the year 2100 in its vicinity, while mouth B is still in 2090 in its vicinity due to the journey. Enter mouth B at its local 2090, emerge from A and its local 2100. Voila, you have jumped 10 years into the future. Or reverse, go in the older mouth and come out the younger, and you've gone to the past. This scenario creates a closed time-like curve, a loop in time where one could, in principle, return to one's own past. This is where those legendary paradoxes rear their heads. The most famous is the grandfather paradox. Could you go back and prevent your own existence? For instance, by preventing your grandparents from meeting, or worse. If you did, who then fired up the wormhole to go back and do that deed in the first place? It's a logical knot that makes our brains hurt. It seems to threaten the very consistency of reality. In a wormhole context, a more immediate paradox might be, imagine sending a message through a wormhole to your own past. Say at noon you receive a mysterious note that says, "Don't go outside at 1 p.m. It has no sender listed. Being cautious, you heed the note, and indeed at 1 p.m. something dangerous falls from the sky outside. Had you been there, you'd have died. Grateful, at 2 p.m. you toss a note through the wormhole that sends it back in time to 11:55 a.m. to your past self, which of course is the note you received. All consistent so far, if a bit weird. But what if instead you decide to create a paradox? At 2 p.m. you send a note back to 11:55 that says, "Ignore this note." If your past self ignores it, you would go outside at 1 p.m. and perish, thus never sending that note at 2 p.m. But if you never send it, you never died, so you would be there to send it. The timelines snarl up. Wormholes thus bring forward the possibility of causality loops, either self-consistent loops, like the helpful note that ensures its own sending, or inconsistent ones, like the ignored warning that prevents its own creation. Many physicists suspect that something fundamental prevents the inconsistent ones. One proposal, the Novikov self-consistency principle, posits that if time travel is possible, only self-consistent events can occur. You can't change events to create a paradox. Somehow probabilities arrange that any action you take was always part of history. In the note scenario, maybe no matter how you phrase it, your past self finds a way to misinterpret or act in such a manner that consistency is preserved. Perhaps you drop the note before reading it, yet still get spooked and stay inside anyway, fulfilling the loop. But others, like Stephen Hawking, felt the universe would enforce something stronger.
a chronology protection conjecture. Basically, nature forbids time paradoxes outright by making it impossible to use wormholes that way. Perhaps quantum effects ramp up explosively as soon as a wormhole becomes a time machine, destroying it or preventing signals from going through in a paradox-inducing manner. Think of it as the universe's emergency failsafe. Whenever one tries to loop cause and effect, physics might intervene with a shower of high-energy radiation or a collapse of the wormhole. We don't yet know the true answer. Our theories are incomplete at this extreme. But let's indulge the imagination with the assumption it could happen. What a strange world that would be. A wormhole could become a literal fate machine. One might see an older version of oneself step out of a wormhole and hand you instructions on how to build your own future. Or two people might play catch with a ball through a wormhole, arranged such that each catches the ball before they threw it. Absurd scenarios that nevertheless obey certain twisted logics. Even the idea of free will is tested. If you enter a wormhole aiming to kill your earlier self, something must prevent you. Perhaps you slip on a banana peel inside the wormhole and knock yourself unconscious, conveniently avoiding the paradox. It's almost comical, the universe conspiring with banana peels to avoid logical impossibility. On the flip side, time loops might allow for closed cycles that don't break logic. Some sci-fi tales imagine a person going through a wormhole, meeting their younger self, imparting knowledge, then eventually aging and doing the same for their next pass. A predestination loop, unchanging but fulfilling itself. If you are inside such a loop, time feels local and fine, but from an outside perspective, it's like a Moebius strip of events. These mind-bending possibilities remind us that wormholes are not just about where, but when. Space and time are interwoven. A wormhole necessarily is a tunnel through space-time, not just space. If the ends move differently, time misaligns between them. Thus, any practical use of wormholes would demand an understanding, maybe even control, of these temporal aspects. One would have to be careful. Sending your ship through might inadvertently drop it in another century. From a narrative perspective, one might ask, is fate alterable if you have wormholes? Perhaps not. Maybe any attempt to change past events either results in failure or was already accounted for. Some theorize multiple timelines could branch. You go back and create a new alternate history separate from the one you came from. But that introduces a whole multiverse of complexity. Let's imagine a more poetic scenario. A person stands before a wormhole mouth, knowing that stepping through will bring them to the past. Perhaps they hope to save someone they lost. It's a very emotional motivation. They step through, find themselves in yesterday. They attempt to change destiny, maybe divert a tragedy. But in doing so, they realize they themselves were the cause of the tragedy in an unexpected way, or they cannot ultimately alter what came to pass in their own timeline. They become, ironically, part of the history they wish to rewrite. There's a somber lesson there. Even with the power of wormholes, perhaps time has a way of protecting itself, or teaching that some events are fixed in the tapestry of cause and effect. On a grander scale, a civilization with wormhole technology might exploit time loops for computation or knowledge, sending answers back to questions before they are asked, gleaning effectively knowledge from nowhere, again, carefully avoiding paradox by consistent loops. It starts to smell of something forbidden, as if reality would tear under too much of this bootstrapping. Indeed, many physicists feel that nature's laws, when fully understood, will prohibit these paradoxes. They suspect either wormholes cannot exist in stable form to begin with, an outcome some hope for to preserve cosmic sanity, or, if they do, using them for time travel will trigger quantum feedback that either collapses the wormhole or otherwise censors the paradox. One proposal: as soon as a wormhole becomes a time loop, virtual particles build up infinite energy, like an amplifier in a loop screaming with feedback, and blow it up, chronology protected by a bolt of infinite thunder. Thus, wormholes and time travel form a delicate dance. If wormholes exist naturally, maybe the universe quarantines them behind horizons or at Planck scales, so nothing macroscopically paradoxical can happen. If an intelligence tries to make one, they might find the second they can send a message to the past, their wormhole self-destructs or fuzzes out. Time travel through wormholes is perhaps the most eerie aspect of all this, because it challenges our fundamental understanding of cause and effect, something we rely on for reality to make sense. It forces questions. Is the universe deterministic and self-consistent, with every loop already accounted for? Or is there an overarching rule preventing loops altogether? In our journey, as we stand at the edge of a wormhole contemplating stepping into the past, we are forced to realize how precious and perhaps inviolate causality might be. That intuitive sense that cause precedes effect, wormholes blur it. It's as if the cosmos hints at a deeper tapestry where threads of time can bend and connect in strange ways, but perhaps only if they weave a consistent pattern. Before our minds fracture under the what-ifs of time loops, let's step back a bit from the brink of paradox. Whether or not wormhole time travel is allowed, the mere possibility draws us into profound contemplations of fate, free will, and the structure of reality. Perhaps, in some layer of existence, all times are one, and wormholes are just tunnels through a four-dimensional landscape where past and future are like different valleys separated by mountains of causality. And maybe, just maybe, those tunnels can only go certain ways, like secret passages that still deposit you in the same castle, not escaping it. However it works out, the prospect of wormholes flirts with time in a way nothing else does. It's as if destiny itself becomes something you could touch or even travel along. And this leads us to wonder, is there a connection between these space-time tunnels and the deepest fabric of reality? Perhaps entanglement and quantum theory, those other puzzlers of cause and effect, have a say in this story. Indeed, a remarkable idea has emerged in recent years, suggesting that entanglement, the quantum link between particles and wormholes, might be two faces of the same coin. Let us now turn to that deep and subtle connection, the bridge, not just through space, not just through time, but possibly the bridge between the quantum and the cosmic. Threads between universes. At the smallest scales of reality, there is a phenomenon as mysterious as wormholes, quantum entanglement. When two particles become entangled, they share a connection that defies classical understanding, a kind of instant linkage where the state of one immediately influences the state of the other, no matter the distance between them. Einstein famously called it spooky action at a distance. It's as if the two particles, once united, remain sewn together by invisible threads, performing a coordinated dance across light years. For decades, entanglement puzzled scientists because it suggested a hidden connection weaving the universe together. Fast forward to today, and an astonishing idea has taken root. What if these quantum threads are wormholes in a sense? What if every entangled pair of particles is connected by a tiny wormhole, a baby Einstein-Rosen bridge, tying them together? It's a bold unification. ER equals EPR, the conjecture goes, meaning Einstein-Rosen bridges, ER, are equivalent to Einstein-Podolsky-Rosen entanglement, EPR. This idea paints a picture of space-time itself as a vast tapestry of quantum threads. Perhaps the reason entangled particles can influence each other is that, in the higher dimensional geometry of the cosmos, they are adjacent, connected by a filament of space. They don't send signals through normal space. They are already one in a hidden sense. Entanglement becomes the fabric from which wormholes are woven. Imagine two electrons born as twins from some quantum event. They fly far apart. Traditionally, we say they remain entangled. If one is spin up, the other is spin down. And until measured, they exist in a ghostly both states blend. Now imagine between them, through the quantum foams,
there's a microscopic wormhole connecting them. When one electron's state is set by measurement, that information doesn't need to travel. The electrons were effectively next to each other through the wormhole, so the other's state is set simultaneously. It's not that a signal flew faster than light, it's that in the hidden topology, there was no distance to cover at all. This is an outrageous concept at first blush, but it resonates with a deeper line of thought. Space-time might emerge from quantum entanglement. Some physicists have found that if you have a highly entangled system of many parts, it can be described by a space-time with a certain geometry. The more entangled, the more connected the geometry. It's as if entanglement is the thread and space-time is the woven cloth. In this view, wormholes are thick bundles of entanglement forging specific tunnels. The poetic significance is profound. Perhaps the universe fundamentally is a web of connections. Separation might be an illusion that is only true on the surface. Beneath, everything is stitched to everything else by threads unseen. If you tug on one particle here, the vibration travels the web and another particle there feels it. Wormholes, then, are not an exotic rarity. They are the skeleton of reality, present in miniature everywhere, binding the cosmos into one coherent whole. It gives a new answer to the longing we started with. The impossibility of distance might be an illusion, because at a deeper level, distance itself is emergent and can be circumvented by connectivity. We've always imagined unity, and it might be that at the quantum level, everything is united in a highly non-trivial way. Consider black holes for a moment. They are extreme objects where quantum and gravity meet. If you create two entangled black holes, for instance by forming them from two halves of an entangled system, it's conjectured they might actually share a wormhole. One might sit in one corner of the universe and the other far away, yet their interiors could be linked. This was part of the reasoning behind ERISEPR, to solve paradoxes about how information escapes black holes. Theorists imagined the Hawking radiation particles outside are entangled with the black hole interior, and that entanglement might be equivalent to tiny wormholes connecting them back in, allowing information to leak out in subtle form. So, entanglement is like a sewing needle. It can stitch space together. Many entangled particles can sew a rich fabric which corresponds to a smooth space. If you tear entanglement, space might tear or become disconnected. This idea remains speculative and theoretical, but it's capturing the imagination because it suggests a deeper truth. Space and time might not be fundamental at all. They could be byproducts of quantum links. The wormhole, therefore, becomes more than a fantastical tunnel. It's the basic thread of the cosmos. Picture the universe as a grand cosmic loom. The warp and weft of this loom are entangled quantum states. The pattern they weave is the geometry of space-time. A wormhole is a particularly bold pattern, a handle in the fabric that ties one region to another distinctly. But in a way, even normal space between any 2 points is filled with countless subtle entanglements that give space its shape. If we follow this reasoning, then creating or enlarging wormholes might be essentially about manipulating entanglement. If two regions of space could be forced into a high degree of entanglement, perhaps a stable wormhole would bloom between them. In labs today, scientists entangle particles regularly. We can even teleport quantum states using entanglement, quantum teleportation. That's not sending matter, but sending information by using entanglement and classical communication. It's not a wormhole travel, but it's a cousin of the concept in the quantum information sense. There's even an experiment in its infancy where a quantum computer simulated a tiny wormhole by using entangled qubits and interpreting the data in space-time terms. It's like making a toy model of EREPR in action. No actual space tunnel was formed in our world, but in the simulated world, it's as if information went through a wormhole. This hints that as our technology with quantum systems grows, we might literally program entangled systems to behave like traversable wormholes for information. Perhaps one day, small amounts of data, maybe the quantum state of an atom, could be transmitted via a sort of entanglement-crafted wormhole, a quantum teleportation on steroids, essentially. If entanglement underlies wormholes, it has a very comforting philosophical implication. The cosmos is profoundly interconnected. The loneliness of those far stars might be an illusion, because in the quantum foam, every particle here is entangled with particles out there from the birth of the universe. In a grand sense, maybe everything is connected to everything by some network of microscopic wormholes, but they mostly average out to normal space behavior, except in special circumstances. This concept is deeply harmonious. It says that the fabric of reality is a unity. Separateness is a state that can be transcended by using the built-in connectivity. It is reminiscent of mystical ideas. All is one, though here in a rigorously specific way. Now, if we accept that entanglement and wormholes are related, it encourages us to think that wormholes aren't just wild solutions we can choose or not choose. They might be required for consistency of physics. They might be how nature keeps the books balanced. For example, a famous conundrum was, if you destroy information in a black hole, which quantum theory says is impossible, where does it go? The EPR answer: it doesn't get destroyed. It's entangled with the radiation and effectively goes through a wormhole out with it. So unitarity, information conservation, is saved. We begin to see wormholes not as an outlandish possibility, but as a necessary feature if certain principles hold. If quantum mechanics is unbreakable and gravity is true, their union might inevitably produce wormholes. Perhaps not large ones normally, but at least quantum ones. The notion of space connectivity being dynamic and multi-layered could be essential to how our universe avoids contradictions. Thus, the threads between universes might not just connect two far regions. They might weave the entirety of existence. The wormhole linking entangled quanta suggests that every time two particles interact and become correlated, a tiny filament of space-time might form. Usually, it collapses quickly and trivially when the entanglement is lost or decoheres into the environment. But when entanglement is preserved, it's as if a glimmer of a tunnel persists. This frames wormholes in a new light, not just transportation devices, but as fundamental bonds. Perhaps love or empathy could be poetically compared to quantum entanglement, connections between distant consciousness that science can't quantify, but nature shows at least in particles. Such bonds shrink distance to nothing. The cosmos might be a grand entangled embrace, and wormholes its literal heartstrings. Before we wax too poetic, let's ground this idea. Experiments hint that entanglement is real. We know it is. And no signals go faster than light in the usual sense. EPR doesn't allow you to use entanglement alone to send a message faster than light either. You need classical info too for quantum teleportation. So even if wormholes connect entangled particles, they can't be used willy-nilly to break causality because you can't control the outcome of measurements to encode a message one way. The universe is clever. It permits the connection, but hides it behind the randomness of quantum outcomes, thus preserving the rule that we can't communicate causally faster than light. Yet, given exotic matter or special arrangements, we might circumvent that by turning a natural wormhole into a traversable one, as we discussed earlier. It might require adding something extra, like coupling two sides with some trick, exactly what those theoretical physicists did to create a traversable wormhole out of an entangled black hole pair. They essentially introduced a tiny interaction between the distant pair, which in effect turned the entanglement wormhole into a signal-capable wormhole. This is on the frontier of knowledge. But the big takeaway for our journey is that wormholes and entanglement hint at a universe where separation is not absolute. The cosmos might be less a collection of isolated islands and more an ocean woven through with currents under the surface connecting them. Now, armed with this perspective that wormholes may be stitched by the quantum threads of reality, we ask, what do our theories of everything, attempts to unify quantum mechanics and gravity, say about wormholes? Are they inescapable, required by consistency, Or do they say, no, you cannot have them? We venture next into the realm of the ultra-small and ultra-high energy, where space and time themselves might fluctuate, to see how wormholes figure into our pursuit of a final theory. Labyrinths of the quantum foam. At the dawn of creation and at the tiniest scales, space and time become turbulent and fuzzy, a concept known famously as quantum foam. John Wheeler, a visionary physicist, imagined that on the scale of the Planck length, about 10^35 meters, space-time is not smooth, but wildly fluctuating, like a stormy sea. Bubbles of space-time could form and merge, tiny wormholes flicker in and out of existence, particles and even baby universes momentarily bud off and reattach. It's a chaotic, frothing picture, nothing like the serene geometry Einstein described at large scales, but rather a quantum maze of constantly changing topology. In this foam, wormholes might be as common as foam bubbles in a breaking wave. However, these would be minuscule and fleeting. They pop in and out, ephemeral tunnels that last perhaps 10^43 seconds, a Planck time. They connect random points, then vanish, often on scales too small for anything larger than a quantum to notice. If one were a tiny quantum traveler, impossibly small, you would see a constantly rearranging maze, a true labyrinth beneath reality's veneer. Now, both string theory and loop quantum gravity, two leading approaches to quantum gravity, have something to say about this picture. String theory posits that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and it requires extra dimensions of space curled up in compact shapes. In string theory, wormholes can exist. In fact, sometimes strings themselves connecting black holes can be interpreted as wormholes. There are also objects called D-branes, and strings stretching between branes could be like wormholes connecting regions. The extra dimensions also allow the possibility of shortcuts. Two distant points in our normal 3D space might be adjacent in a higher dimensional space, similar to our folded paper analogy, meaning a wormhole could take advantage of those hidden dimensions to cut through. String theory's mathematics is so rich that exotic space-time topologies are part and parcel of it. There's a sense that string theory wants space-time to be malleable and connected in complex ways. Loop quantum gravity, LQG, on the other hand, attempts to quantize space-time itself by breaking it into finite loops, like a spin network. In LQG, space is discrete at tiny scales, woven from loops like a chainmail. In such a scenario, the connectivity of space can change as the network of loops rearranges. It's plausible that LQG permits topology change. Essentially, the network could rewire, making a handle, wormhole, appear or disappear. Some studied solutions in simplified models show that wormhole-like structures can emerge. The discreteness might smooth out infinities that plague wormholes, like the singularities, making a traversable wormhole solution more feasible under some circumstances, at least mathematically. Holography, the concept that our 3D universe might be described by information on a distant 2D boundary, like a hologram, strongly suggests that geometry is an emergent thing. In the holographic ADS-CFT correspondence, a gravity theory in a volume is equivalent to a non-gravitational quantum theory on its surface. In that context, a wormhole connecting two spaces, like two black holes in the bulk, corresponds to an entangled state in the boundary theory. We already touched on that with ER-EPR. Holography thus practically shouts that if entanglement is present, geometry will reflect it, meaning, again, wormholes are a natural piece of the story. One striking development, in calculating black hole entropy and evaporation, the information paradox, theorists found that including wormhole-like contributions, so-called replica wormholes, in Euclidean path integrals, fixed certain results to align with unitary evolution. This technical result basically says, when summing over possible histories of a black hole, quantum evaporating, histories where wormholes connect different copies of the black hole, used as a mathematical trick, dominated and gave the right answer. It's as if the universe uses wormholes behind the scenes to preserve consistency and information. This hints that, in a full quantum gravity, wormholes are not only allowed, they're needed. So, what do these labyrinthine theories imply? It seems that any consistent theory that merges quantum mechanics and gravity either allows ephemeral wormholes naturally, quantum foam, or equates wormholes with fundamental quantum correlations, holography, or at least doesn't rule them out and maybe includes them in certain solutions, string and LQG. It could be that wormholes are required by nature's consistency to glue space-time together at the seams, or to ensure information is never truly lost. If one tried to eliminate wormholes entirely, one might end up with an incomplete theory. They might be the glue between separate regions of space, or even separate universes. Speaking of separate universes, some theories entertain that our universe might not be alone, and wormholes could connect to other universes entirely, a concept of baby universes branching off, or parallel worlds connected via tunnels. If space can connect distant points, perhaps it can connect different cosmic regions that are otherwise disjoint. A wormhole mouth in our universe could potentially be a gateway to another universe's region if such a handle was ever formed in the greater multiversal space-time. This remains speculative, but when we talk about various types of geometry on either mouth, as some theoretical work mentions, it includes the wild possibility that each end is in a separate cosmos. Another context: cosmic strings or other defects from early universe phase transitions could theoretically get tangled and form loops, possibly leading to wormholes or being used to create them via their gravitational effects. The early universe was a high-energy playground. Some think wormholes could have been naturally produced then, either lasting if exotic conditions existed or evaporating quickly. One humorous way to think of the Planck scale foam: it's like the sewers and catacombs beneath a city. We normally traverse the streets, our conventional space, but down below is a hidden network. Most of the time, it's inaccessible or unhelpful for going far because it's messy and unpredictable down there. But if one could map those catacombs or enlarge a passage, you might pop up somewhere far across the city, out of a manhole, surprising everyone. The Planck foam wormholes are like those catacomb passages. They usually are tiny dead ends, but who knows, perhaps one or two connect deeper than we expect. When we build particle accelerators or attempt to probe small scales, we might inadvertently tickle this quantum foam. Some have even mused, could high-energy events create a wormhole? It's extremely speculative and not supported by evidence. Micro-black holes remain hypothetical too, at accelerators, let alone wormholes. But the fact the math doesn't forbid them means we keep watchful. In the language of loops and strings, a wormhole is a non-trivial topology. There's a concept known as topology change, where space-time can go from one shape to another. Many quantum gravity calculations allow topology change at tiny scales. If real, it means space is not a fixed stage, but can tear and reconnect. So a region could split into two, a baby universe splitting off, or two regions merge, a wormhole mouth connecting. Most of these would happen at safe, microscopic scales and average out to a smooth, large-scale reality. But if one could amplify such an event, a macroscopic wormhole might appear. The dream of theoretical physics is to have a single framework that describes all this, one where we see clearly how quantum foam yields the stable cosmos we inhabit, and whether wormholes can stabilize out of the foam or not. We are not there yet. But glimpses from these theories suggest wormholes are not just artifacts. They might play roles in deep questions like, what is space? And how is information preserved? If wormholes are indeed deeply woven into quantum gravity, it means that any sufficiently advanced manipulation of gravity at quantum scales might access them. It's as if the locks are there,
and we just need the right quantum key. It could be that civilizations eons ahead, with mastery of Planck-scale engineering, could pluck a wormhole out of the foam, like pulling a thread from fabric, and sew it into a larger, stable tunnel. Imagine having a machine that generates a pulse of something that coaxes a tiny wormhole to grow rather than vanish, feeding it negative energy, sculpting it open. This is the holy grail of wormhole science fiction, artificially creating wormholes, effectively building cosmic subways. Whether that's possible or forever out of reach, our theories are not yet decisive. They tantalize us with maybe. However, there's an even bigger picture. The entire cosmos itself might be riddled with wormholes, not by accident or design, but as a consequence of how it started or how it is structured. Let's explore that possibility. Could the large-scale universe contain wormholes naturally? And if so, how would we find them? Cosmic gateways and shadows. The universe is vast and mostly empty, but perhaps not entirely featureless. We often consider only galaxies, stars, and dark matter clumps affecting the motion of objects. But what if, hidden among the galactic halos or the cosmic web, there are wormholes? Naturally occurring portals strewn through the cosmos, relics of the very early universe or spawned by rare astrophysical phenomena. What evidence might we see? How would they shape the cosmos at large? One line of speculation. If wormholes formed in the chaotic conditions of the Big Bang or during early cosmological phase transitions, some might persist. These primordial wormholes could connect regions of the universe that are now far apart. They might even be responsible for certain puzzling observations. Say, an unexpected correlation between distant parts of the cosmic microwave background, or unusual gravitational lensing events that can't be explained by visible mass or even dark matter distribution. Consider gravitational lensing first. A wormhole mouth, if large enough, has gravity, but not the same as a black hole. It doesn't have an event horizon trapping light. It could lens light in weird ways. For instance, light passing near one mouth could enter it and exit out the other, arriving from a completely different direction than expected. This could produce exotic lensing signatures, double images of a quasar where one image is normal, light that traveled outside the wormhole, and another is actually light that went through the wormhole and out another mouth. Or perhaps a peculiar distortion or flux anomaly in lensed galaxies that can't be matched by any standard mass distribution. Some theoretical papers propose specific lensing patterns that would be telltale wormhole fingerprints, perhaps like an Einstein ring with strange intensity variations. Another clue might be in the motion of stars. Picture a star orbiting seemingly nothing, not a black hole. We'd detect emissions or something at least, but the gravity is there. It could be orbiting one mouth of a wormhole, feeling the gravitational pull of both the mouth itself and possibly mass on the other side of the wormhole, mass that lies in another galaxy, for example, but connected gravitationally through the wormhole. If, say, on the far side mouth there's a star cluster, their gravity could reach through and perturb orbits on this side in a way that doesn't match just local, visible mass. So astronomers could find a system where gravity seems to emanate from an empty region with a weird pattern. It might not match a simple dark matter clump either. Speaking of dark matter, some have indeed speculated that wormholes could masquerade as dark matter. Maybe what we call dark matter includes some wormholes that effectively add gravitational effects without light. It's a stretch. The current dark matter paradigm leans toward particles, but exotic alternatives have been entertained. For example, an extended wormhole mouth might mimic the gravitational profile of a massive, diffuse object. There were studies exploring traversable wormholes sustained by dark matter. Conversely, maybe the concentration of dark matter in galaxy centers could fuel wormholes if dark matter has some unusual pressure characteristics. One particularly striking idea: our Milky Way's center hosts a supermassive black hole. Some theorists asked, could that black hole actually be a wormhole mouth? If one fell in, could you emerge elsewhere? We have near-future tests, precise observations of stars, like the famous star S2, orbiting the galactic center, can tell if the central object has properties slightly different from a textbook black hole, like a tiny reflection or oscillation from something coming through, albeit that seems unlikely. One idea was if our black hole was a wormhole, perhaps particles entering might come out as an outflow somewhere else, potentially affecting things like jets or gamma-ray emissions in a peculiar way. So far, no such deviations have been clearly spotted. The evidence points to a normal black hole, but it's not completely closed yet. Another observational handle: cosmic ray anomalies. If a wormhole connected two very different regions, high-energy particles from one side could appear seemingly from nowhere on the other. Imagine detectors on Earth catching particles with signatures that suggest they originated from, say, a supernova, but in a direction where there is no supernova, or only a distant one too far to be likely. Could they have hopped through a wormhole? This is highly speculative, and identifying that is incredibly hard, given how varied cosmic rays can be. Then the cosmic microwave background, CMB, the afterglow of the Big Bang. It's mostly uniform, with slight fluctuations. If wormholes were around then, they might have caused weird patterns, like repeating spots or unusual alignments. Some people in Fringe speculate features like the cold spot or certain alignments in the CMB could be due to cosmic textures, defects, maybe even wormholes or cosmic tunnels affecting the last scattering surface. No evidence solidly points to that, but the thought is out there. In cosmology, there's also the notion of the universe being multiply connected. For instance, if you travel in one direction and eventually come back from the other side, like a Pac-Man game screen, leaving one edge and entering from opposite edge, that's a closed topology. Wormholes could allow such pseudo wraparound effects. The universe might be finite and connected in a complex way, rather than just straightforward. If we saw the same galaxy's image repeated in opposite parts of the sky, that could mean the light went two different routes around a connected topology. That's somewhat different from a localized wormhole, but conceptually related if space overall has a non-trivial topology. A bold scenario, perhaps inflation, the rapid expansion of the early universe, created wormholes. Usually, inflation would blow them apart. You might think any tiny wormhole either got stretched to enormous scales or pinched off. Some calculations show inflation could either dilute wormholes to negligibility or in some cases amplify them. If any persisted, inflation's end could have left a network of large wormholes scattered about. They might be extremely rare, but even one in a Hubble volume would be fascinating. If the universe had natural wormholes, they might serve as cosmic subways for advanced life or for matter itself. One could envision extremely old civilizations mapping them out. A hidden, cosmic web, different from the galaxy filament web. A web of tunnels linking galaxy to galaxy. Perhaps one reason we haven't seen aliens zooming around is because they use wormholes which are not visible as bright rockets. They slip in at one location and out at another. From a more grounded perspective, searching for wormholes is part of searching for any new physics. So far, no clear evidence, but it's something that occasionally appears in serious literature. If wormholes exist, here's how we might detect one. We might not have recognized an anomaly for what it is yet. One surprising connection: some black hole solutions hint at the interior maybe being a sort of wormhole. For example, the maximal extension of a Schwarzschild black hole includes another universe connected by the singularity. But in reality, you cannot traverse it because the bridge exists only for an instant before closing, and singularity prevents crossing. Rotating black holes, Kerr, in theory, have a throat leading to other universes or distant parts, but unstable and likely closed by perturbations. Still, mathematically the solution has a door. That door likely slams with slightest disturbance, and nature always disturbs things. So observationally, black holes behave as one-way traps, not two-way wormholes.
Dark matter's gravitational influence is well documented and largely explains rotation of galaxies, etc. But if a wormhole were present, it would be highly localized effect, whereas dark matter is spread in halos. Could a wormhole connect the centers of two galaxies' halos? Then maybe dark matter flows or is shared, but that's stretching. Perhaps wormholes could connect not just places in our space, but different epochs. A wormhole that links the present universe with a much earlier era of universe. Could dark energy, the mysterious accelerated expansion, be related? Maybe not directly. Dark energy is like a property of space causing acceleration. But interestingly, the exotic matter needed for wormholes, negative energy, is somewhat conceptually related to dark energy. Though dark energy is positive energy with negative pressure, not quite the same as what holds a wormhole open in most models, which is negative energy density. Some weird theories consider wormholes as an explanation for certain dark energy phenomena, or vice versa. Let's imagine that indeed some wormholes are out there. We could search for their gravitational wave signature too. Perhaps the oscillation of a wormhole mouth might produce gravitational waves different from merging black holes. Or if something travels through a wormhole, does it ring space-time? Possibly. If a star fell through a galaxy's wormhole, you'd see the star's light vanish. Maybe we'd detect unusual gravity waves from the event. So far, nothing like that has been seen, but our instruments are improving. It stands as one of those keep an open mind aspects. If one day we see an effect we can't explain by black holes or neutron stars or dark matter particles, maybe we'll consider wormholes. Given the lack of evidence, one might lean to thinking cosmic wormholes, if they exist, must be extremely rare or hiding very well, maybe near black holes or masquerading as them. Or maybe there are none until someone or something makes them. This brings us to the cusp of speculation turning into aspiration. If nature doesn't readily hand out convenient wormholes large enough to use, might an advanced intelligence create or enlarge them? We touched on how it might with exotic matter and quantum engineering. Now let's explore that more fully. The concept of artificially made wormholes versus natural ones, and what it means for those who wield such power or stumble upon it. Forging the cosmic ladders. Imagine a future where science has advanced unimaginably. Perhaps humanity, or some other species, has unlocked the secrets of quantum gravity. In gleaming facilities orbiting dying stars, or in the cold of intergalactic space, they work on the grandest engineering project of all, building a bridge through space-time. Artificial wormholes become the stargates of science fiction lore, but rooted in painstaking physics. How might one go about it? We earlier described the theoretical recipe. Gather colossal amounts of negative energy or exotic matter, manipulate space-time with precision, possibly using ultra-strong magnetic fields, laser-cooled vacuum fluctuations, or harnessing phenomena near black holes. The endeavor might start small. Quantum wormholes for information transfer. Then perhaps send subatomic particles through micro-wormholes. Slowly scale up, solving one unforeseen issue after another. Radiation instabilities, quantum fluctuations trying to break the tunnel, etc. One could use black holes as part of the machinery. Perhaps two small black holes are entangled from their formation and then charged with negative energy, gradually transforming their connecting interior into a traversable throat. Or one could try to inflate a wormhole from the foam by injecting energy in just the right way, like how in lab we can sometimes coax a virtual particle pair into real particles by applying a strong field. If a tiny wormhole flickers into being in the foam, zap it with a blast of Casimir-induced negative energy to freeze it in existence longer, then reinforce it, a bit like catching a bubble with a freezing spray so it doesn't pop. The ethics and caution here would be enormous. A miscalibrated wormhole could collapse catastrophically, maybe releasing a blast akin to a supernova as all that energy gets dumped into normal space. Or if it connected to somewhere undesirable, near a supernova or active gamma ray burst,
one might inadvertently flood their region with lethal radiation. It would be the ultimate risky experiment, playing with cosmic fire. Yet the payoff, instantaneous travel across the stars, is so great that one suspects any sufficiently curious species would attempt it eventually. It's the kind of project that might define a civilization's epoch, like our Apollo program times a million. The existence of artificial wormholes raises profound questions. Would they be regulated? Would they be weaponized? A wormhole could theoretically be a weapon, dropping an enemy into a sun, or opening a hole from near a black hole to their planet, hurling intense radiation or tidal forces through. It's a terrible and potent possibility. The ethics of wormholes would be as complex as the ethics of nuclear arms, if not far more. Perhaps an advanced society decides that natural wormholes, if found, are safer to use than making new ones, akin to using existing tunnels rather than blasting new ones through a mountain that might cause avalanches. They might search the cosmos for extant wormholes, like we search for natural resources, and stabilize or enlarge them. Who knows? Maybe they've been out there doing so, unseen by us. From a philosophical and existential standpoint, the ability to create wormholes would make a civilization nearly godlike in mobility and reach. Distance and time become trivial obstacles. Such a civilization could spread its influence instantaneously to many worlds, forming a true galactic or even intergalactic community. They could also retreat into pocket universes or create sanctuaries connected only by their controlled wormholes, walled gardens of reality. The presence of artificial wormholes might also leave artifacts. What if some cosmic phenomena we see are actually ancient wormhole endpoints left by now vanished civilizations? Perhaps some unusual radio sources or unexplained bursts are the dying breath of a wormhole that's oscillating or closing. One interesting concept: wormhole communication versus transportation. Maybe it's easier to send signals or data than to send people initially, like how telegraph cables preceded human travel across the ocean. A small wormhole might only allow light or quantum states through, effectively a galactic communication line beating any normal signal. You could have a real-time conversation with someone tens of thousands of light years away via such a quantum phone line. The bandwidth might be small at first, maybe only qubits per second, but even that changes things. Then in time, larger wormholes for sending physical objects or people. Perhaps giant space stations anchored to wormhole mouths, serving as ports. Commerce, exploration, diplomacy, all transformed. But such mastery also forces introspection on meaning. If you can go anywhere instantly, does the journey lose meaning? Do distinct cultures homogenize into one? Does the universe become like one singular place, rather than billions of isolated islands? There's beauty in bridging divides, but some would lament the loss of cherished solitude or uniqueness of far-flung places. There would also be those who fear wormholes, each one a potential Pandora's box. Could something dreadful come through? Could an unknown plague or hostile force use it? The decision to open a wormhole to an unfamiliar region is momentous. It's like opening your front door to the entire universe and not knowing who might knock. We might also ask, would a civilization allow open public use of wormholes, or keep them extremely controlled? Possibly extremely controlled for safety. One malfunction could even perhaps distort space-time in an area, affecting orbits or causing a collapse, harming nearby systems. Then consider if wormholes allow time travel. Some configurations would. That would necessitate even stricter regulation, or possibly a technical design that prevents time paradox use. E.g., maybe they only allow synchronously moving mouths, like always keep them in equal gravitational potential and not moving relative, so time stays aligned. On the flip side, perhaps natural wormholes, if any, aren't so cooperative. They might inherently allow time differences. An advanced civilization might then attempt to sabotage wormholes that risk time paradoxes. Possibly some law of physics or society forbids connecting two wormholes in a way that makes a loop. In fiction, wormholes often serve as gateways to adventure.
but also to existential threats, like unknown monsters or invasions. In reality, any species messing with wormholes must also be prepared to possibly encounter others via them. A wormhole could be a two-way road to an invasion, intentionally or not. However, if we imagine a benevolent, wise usage, wormholes could connect realms of knowledge. A library planet containing records of millennia, accessible to any other world via a portal. A medical station reachable instantly from anywhere suffering a pandemic, sending doctors through to provide immediate aid. It's a vision of a truly interconnected, almost utopian arrangement, assuming goodwill and competence. There's also the spiritual aspect. Bridging cosmic gulfs might make beings feel unlimited and perhaps diminish the appreciation of distance, or, ironically, increase appreciation because one can go see these wonders firsthand easily. The night sky would no longer be a symbol of unattainable mystery, but an attainable destination. Some thinkers might worry, if we overcome all boundaries, do we lose something important, the striving, the dreaming, or do we simply find new frontiers, like different universes, or deeper into quantum realms or inner journeys? Likely curiosity never ends. Wormholes would just expand our playground. Now, consider a species that discovered wormholes early. Perhaps aliens millions of years older than us have been quietly using them. They might have a whole invisible infrastructure threaded through the galaxy, hidden from our detection so far. If one day we stumble on one of their gateways, how awe-inspiring and terrifying would that be? It's one thing to theorize wormholes, another to find an actual shimmering portal left behind by unknown hands. One could imagine a scenario where humans in the near-ish future detect an anomaly in space, investigating. They find it's a stabilized wormhole with an entrance near our solar system, origin unknown. Does humanity dare to step through? What if it leads to the ruins of an ancient civilization, or directly to an inhabited system far away? It would be a leap of faith, and potentially a leap into the lion's den. Or we might create our own small wormhole labs and inadvertently signal our presence to advanced wormhole-using species by the exotic energy signatures. Perhaps a friendly elder race then reaches out through a wormhole to greet us or warn us. In any case, the creation of wormholes, or even their discovery, would mark a turning point, a threshold after which existence is fundamentally different. It is literally a crossing from one era to another, just as stepping through a wormhole crosses from one place to another. Finally, beyond the logistical and ethical, there's a grand philosophical resonance. Making wormholes is essentially uniting what was separate. It's an act of cosmic love, in a sense, bringing together distant parts of creation. It speaks to a desire to overcome not just physical distance, but any separation, perhaps reflecting the deepest drive of intelligent life to connect, understand, and not be alone. And so, as we stand on the precipice of such potential power, we reflect. What does it mean that we sought these cosmic ladders? What does it say about our nature and about the nature of reality that such ladders can exist at all? In our final reflections, we return to the human condition. Small creatures on a pale blue dot, dreaming of bridging the stars, and by doing so, perhaps learning something profound about ourselves and the universe. Reflections at the threshold. At the end of this long journey, from ancient dreams to the cutting edge of physics, we find ourselves gazing into a mirror of sorts. Wormholes, those enigmatic bridges, have been our focus. But what they reflect back is the timeless human narrative of yearning to transcend limits. We see in them an echo of every boundary we've ever wished to overcome: distance, time, ignorance, even death. Why have wormholes captured our imagination so deeply? Perhaps because they symbolize hope against impossible odds. The universe is overwhelmingly vast. The speed of light an iron gate. Death and time irreversible. These are the cold realities. And yet the wormhole whispers, maybe not. Maybe there is a secret tunnel,
It's a crack in the wall of determinism, a suggestion that no prison is perfect, not even the prison of being confined to one moment and one place. In a wormhole's existence, if it indeed exists, lies a philosophical message that separation might be an illusion, that for every here there is a path to there, for every then a path to now. It hints that the divisions we take for granted, me versus you, earth versus sky, past versus future, might be united at a deeper level. Consider the boundaries we face in life. The ocean horizon that stopped ancient explorers until ships were built, the sound barrier until jets broke through, the gap between continents until radio waves spanned them. Each time, when a boundary falls, our perspective enlarges, and we realize that what separated us was not insurmountable. Wormholes represent the ultimate boundary dropping, the end of isolation by space and even by time. And what then? If one day we open such doorways, we might come to see ourselves not as many isolated civilizations on distant specks, but as one community in a connected cosmos. The universe itself might be experienced as one grand home rather than a vast, unbridgeable wilderness. The psychological impact would be profound, awe certainly, but also perhaps a peace that comes from knowing the gulfs can be crossed. On a personal level, the wormhole is a lovely metaphor for relationships and understanding. When two minds connect deeply despite distances of culture or upbringing, is that not like bridging worlds? When empathy lets us feel another's pain as our own, we have in a sense created a little wormhole between hearts, collapsing the distance of otherness. The entire scientific quest for wormholes could be seen as an extension of our innate drive to connect, to not be alone. Of course, there's also the lesson of caution. Not all boundaries are meant to be crossed heedlessly. There is a natural order, and wormholes, if misused, could create chaos, like the time paradoxes. Similarly, in life, breaking boundaries without wisdom, ethical boundaries, for instance, can lead to trouble. So perhaps wormholes teach us the value of responsible freedom. The door can open, but should it, and when, and for whom? These are questions as important as how to open it. We might also glean something about illusion and reality. Wormholes make us question the solidity of distance. If two distant stars can really be adjacent through a higher dimension, then what else about reality is merely perspective? It invites an almost spiritual contemplation. Maybe separateness is a kind of cosmic mirage, and underlying it is unity. For some, wormholes are scientific. For others, they parallel mystic notions that everything is one. It's fascinating when physics hints at philosophical truths long pondered. Then there's the interplay of discovery and humility. To even consider building wormholes, we must harness forces we can barely imagine and fully understand natural laws. It's a huge intellectual triumph, and yet it would show us how much more there is beyond. Perhaps there are higher order connections beyond wormholes, or entirely new dimensions of existence. Each horizon reached just reveals a new ocean beyond. In standing before an open wormhole, one might feel what astronauts describe seeing Earth from space, the overview effect, a cognitive shift where boundaries fade and a profound sense of the unity of life and the fragility of our tiny world hits home. With wormholes, the overview effect might extend to the galaxy or the universe, seeing all of it as one tapestry. Perhaps then we treat our universe more gently, more reverently, knowing how intimately it's all connected. We started with the impossibility of distance and the longing to bridge cosmic gulfs. That longing drove mythmakers to imagine rainbow bridges and gods traversing the sky. It drove physicists to scribble equations that pierce the veil of reality to reveal hidden tunnels. It drives current scientists to entangle particles and dream of quantum gateways. It drives storytellers to spin tales of star portals and time machines. And maybe one day it will drive explorers through an actual wormhole to shake hands or appendages with beings under another star's light. In a sense, the wormhole was within us all along. As a concept, it lived in our collective psyche, urging us onward. It is the ultimate manifestation of the bridge-building impulse that gave us language, culture, internet, and all connections. And if one day we find that the cosmos indeed permitted such bridges, it will feel like a dialogue between us and the universe. We asked, in our poetry and our equations, can we connect? Are we allowed to defy this separation? And the universe, through subtle hints and finally through technology, answers, yes, with wisdom and wonder, you may. In the end, wormholes are as much a story about us as about space. They encapsulate our ingenuity, our daring to ask, what if? Our refusal to accept imposed limits, and also our need for each other and for the other worlds we long to know. Whether wormholes remain forever theoretical or become concrete travel corridors, they have already served as bridges, connecting ideas across disciplines, connecting science with imagination, and connecting our present understanding with the deeper truths of reality. As we conclude this odyssey, picture once more the night sky. Once, we saw mostly emptiness between the stars, a forbidding void. Now, after exploring wormholes in concept, perhaps we can imagine faint silvery threads crisscrossing that darkness, hinting that the universe is secretly knit together, just waiting for us to find the stitches. The distance was impossibility only in our limited view. Lift that veil, and distance may be no more defining than the space between letters in a word, all part of one meaningful pattern. We stand at the threshold of that understanding, filled with reverence. The cosmos feels a bit more intimate, its mysteries a bit more within reach, yet still as majestic as ever. Wormholes or not, we belong to this universe, and maybe, through our thirst for knowledge and connection, this universe reaches back to us. In the silence after such grand thoughts, one might hear an echo, perhaps the whisper of an ancient myth or the hum of a quantum particle, both saying the same thing. All is connected. And so, with hearts full of wonder, we step back from the edge of the wormhole and carry that truth with us as we continue our journey through a universe that is stranger, more mysterious, and more beautifully connected than we ever dared hope.